Great. Well, good morning, everybody, and a very big welcome to this workshop on albedo enhancement and refreezing the Arctic. It's being hosted by the Centre for Climate Repair. We are an institution within the centre of Cambridge, but we work with many other institutions around the world, different universities and non-universities alike. I'm going to let Hugh actually give an introduction to the Centre for Climate Repair. But what I wanted to do was just explain the format and the forum for this morning was inspired about 4 weeks ago, because one of the people that we work with and talk regularly with, Robert Tulip, all the way from Australia, said he's coming to Cambridge, and therefore actually using that as a sort of a trigger point, say, could we actually organise a workshop on this theme? So that's what we've done. And what I'd really like us to do today is to focus on that word workshop. So we have a number of people online, we have a number of people here in the audience, and if you think about sort of the different personalities and different characteristics, what I would really like is, I know Hugh has let people know that those people who are effectively presenting to keep those presentations to 10 minutes. What I would also like us to think about is the elevator pitch. And I remember that when I was pitching for sort of some investment, I remember it was on a Saturday morning in Grosvenor Square, and there was a guy called James Kahn from Dragon's Den, and you know, we were told the format was 20-minute presentation, and then 15 minutes before we were due in, they said, "Oh, sorry, James is running a bit late. It's only a 10-minute presentation. Is that okay?" And then 5 minutes before we were due in, Shaun, it's only 5 minutes maximum. And then as we walked in, he said, "Shaun, we don't really want a presentation at all." And actually, it ended up being very, very valuable, because it was more of a conversation. And actually, the conversation was rather more stimulating than a presentation. So I'd just like to share that experience with you, so that when we are in discussion mode, I would like us to try and be really diligent and hard on ourselves to try and keep our contributions if you're saying something. And I know I've already broken the rule, all right? But I was one of the presenters, so I'm allowed up to 10 minutes, but I'm taking less than that, to keep our contributions to no more than 2 minutes, right? Because that way we'll have interjections and the energy levels in the room will be much greater, and we'll be able to invite and solicit opinions and views from other people. And it's really important that we sort of have multiple views on a given topic today. Otherwise, it isn't a workshop. So with that, I'm going to now hand over the baton to my very dear colleague, Professor Hugh Hunt, to give an introduction to climate repair. Thanks, Hugh.
Thanks, Shaun. Shaun, perhaps you could just make sure that anyone who wants a copy of the program, paper copy. Well, look, it is great to, we have had some pretty difficult times over the last few years, and we're beginning to get back to doing things face to face. One of the virtues of having chosen today for this event is that just yesterday, the final year engineering students here in Cambridge gave their last undergraduate presentation, and you're going to hear 2 of those presentations this morning. And then we've also got a couple of our PhD students giving presentations. So everything is all lined up nicely for a good day. The most important thing for me is about the discussions we will have. So that's why we're keeping the presentations short, and to allow plenty of opportunity for chatting. Now, the Centre for Climate Repair began about 3 years ago here in Cambridge, founded by Sir Dave King, who gives his apologies. He's down in London today, trying to get rather a large amount of money into this subject, which is a good thing to be doing. But we were set up in Cambridge, based at Downing College, and Downing was very, very generous in hosting us for a couple of years, before, just until really 2 months ago, we've grown too big for Downing College, and we're now set up in the university. So the Centre for Climate Repair is based in the Department of Applied Maths, but we've got a strong presence in the Department of Geography, the Department of Engineering, and Department of Earth Sciences. And we're trying to spread into as many disciplines as we can, because we know that climate repair is not just about climate science. We are trying to emphasize the scale, the engineering scale of what is required, and also in the areas of ethics and governance and the social side, because we've learnt, for instance, from the people at Southern Cross University in Australia who are doing work on cloud brightening to cool the waters around the Great Barrier Reef, that engagement with the indigenous peoples in and around the Great Barrier Reef has been very important. And that engagement began 10 years ago or even more. So if we are going to be doing things in the Arctic or elsewhere with a view to cooling the Arctic or whatever else we might want to do, engagement with the indigenous peoples in the region is pretty important. So we want to be setting up our Centre for Climate Repair with those connections in mind, as well as just the science and engineering. I shouldn't say just the science and engineering, because they're pretty big topics. So the Centre for Climate Repair has three big messages. One, and we call them the three R's. R for we've got to stop burning fossil fuels. So I've forgotten what the R stands for. We've got to reduce our emissions. And that's a given. And actually reducing our emissions is so much a given that it's part of what we do. Perhaps we work on emissions reductions from the built environment. But the next R is removing CO2 and other greenhouse gases from the atmosphere. And we're looking at the oceans as a source of CO2 and how to improve, to restore the oceans. And we're looking at methane as a greenhouse gas, how we can oxidize methane, atmospheric methane, and perhaps methane higher concentrations around the place. And then the third R, refreeze, repair, restore. Lots of R's we can use here, but we've landed on refreeze because the Arctic and the Antarctic are both vulnerable, and the Himalayan glaciers and elsewhere. So there are three big things, and we are really so lucky to have in Cambridge smart students, smart postdocs who really want to be working in this area. And we want to act as a focal point for this kind of research. So that really is what led to this workshop today. And thanks very much to Robert. And just so everyone knows who Robert is, he's waving his hand over there. Robert is from Canberra, a lovely, quiet little town in the middle of New South Wales, the capital of Australia. Great to have you here, Robert. Thanks for precipitating this meeting. So what we will do is, I think the best way to learn about what the Centre for Climate Repair is doing is by hearing by some of the stories, both from online presenters and from people here. So the first one we're going to do, Mike, by the way, huge thank you to Mike, who's up in the booth up there. We've got a newly fitted out technological system here, which I think we might be using for the first time. Is that for the first time? Yep, this is the first run of this new system. So it's great to have Mike doing the technology for us here. So what I thought we'd do is move straight on, short presentations, then time for a few questions after each presentation, and then discussion, how do things pan out? So we've got on the list first is an online presentation from Isabelle Steinke. And now, how do I have to do anything here, Mike, or are you going to? What do I do?
Should I just start sharing?
There we go. There's Isabelle. We can see you there. Isabelle, we can hear you, Isabelle.
Just a
Is that-
second. Let me just share my screen. Put this into full screen. So can you hear me well?
Yes, we can. So Isabelle is in the Netherlands at Delft University and is part of the Refreeze the Arctic Foundation. We have funding from the Refreeze the Arctic Foundation for our collaborative work. And by the way, the RAF, last night we were in the RAF bar at the Eagle pub. So that was Royal Air Force and Refreeze the Arctic Foundation coincidentally have the same acronym. Right, Isabelle, over to you.
Thank you very much for having me. So as Hugh rightly mentioned, I'm talking on behalf of my colleagues at TU Delft. So that would be Pierre Siebesma, George Biscoff, Stefan de Rode, and Hermann Ruschenberg. And what I'd like to do with this very short talk is just give you an impression of two concepts which are related to radiation management, so atmospheric climate engineering. First, starting with the one that Hugh has already mentioned, so marine cloud brightening, that is work that is funded by the Refreeze the Arctic Foundation, and then leading over to a different proposal for climate engineering, which is related to a different kind of clouds. So that's the agenda for today. And let's just dive in straight away. So as I was saying, there is lots of different proposals for climate engineering, but what I'd really like to discuss is two of those proposals which are related to clouds. And just for everyone in the room, what are clouds, or what is a cloud? So clouds are a very, very complex part of our climate system because of their radiative impacts. And they're also a very delicate part of the hydrological cycle, which is something we should keep in mind when you talk about radiation management based on clouds. And just to give you an idea of how clouds form, so what is needed for clouds is really thermodynamic conditions, but also tiny particles on which of those clouds grow. So we have droplets and ice crystals in those clouds. And these are basically also the effects that we're going to leverage to change the structure of clouds in order to then change their radiative properties, which is essential if we want to achieve a cooling at the surface. So what you can see here on the right-hand side is a satellite image of clouds over the ocean. And you can see very many different structures. So one is those clouds which are more covering larger areas. And then you see those wriggly lines. And those wriggly lines are ship tracks. So those are clouds which are essentially caused by exhaust from ships. So what happens is that those ships, they burn their fuels and they emit tiny particles. And onto those tiny particles, we have water condensing. And that gives clouds. And as you can see, those clouds are very bright in comparison to the ocean surface, which is dark here. So that means that those clouds are scattering back a lot of sunlight, which also means that we're taking energy out of the system. And the idea between deliberate interventions into clouds here is that we produce clouds over the ocean through ships, and thus increase this radiative effect, scattering more sunlight back to space. So one of the proposals here is to use material that is already there in the ocean, and that is spraying tiny sea salt crystals into the atmosphere, so into the boundary layer, and then create clouds that way, and have more reflective clouds produced from those salt crystals, which get sprayed into the boundary layer. However, that's a very, very tough challenge, actually, because that effect, so having really the right size of cloud droplets, and also having clouds that persist for long enough, is very challenging, and that is because it's really size dependent. So it depends on the size of the sea salt crystals that able to produce. Because if you have very large cloud droplets, that means that your cloud just rains out very fast and it disappears. So that's one side. And the other side is that if we have many small seeds, that leads to very increased evaporation, and we also have thinner clouds on the side, because we have direct radiative effects of those salt crystals. So essentially, it's a very tricky challenge to get the size of the sea salt crystals exactly right, so that we get persistent clouds with also the desired radiative effects. And as I mentioned, we're working with the Refreeze the Arctic Foundation and in close collaboration with the teams of Hugh and Shaun. And this is really to tackle marine cloud brightening from a broader perspective. So what you can see here is really different areas in physical sciences and engineering that we need to tackle. So I talked a bit about the cloud processes, which are really important to understand and target marine cloud brightening. But as you can see, there is also the generation and delivery aspect, which is a huge engineering challenge, as I mentioned, because we really need to get those sea salt crystals in the right size in order to have the desired effect. And what we're not even touching here in this discussion is really how many clouds are really susceptible to this kind of seeding, because also the ambient conditions need to be right. And then also if we cool a larger area over oceans, that would have impacts on the whole atmospheric dynamics as well as obviously on the marine ecosystems, because if you cool a substantial area, that will also have impacts on the living creatures in the ocean. So these are all aspects within a wider context of marine cloud brightening, which we should consider. So just summing up, so this is a very complex research question, whether marine cloud brightening can be effective and whether it's also desirable. So as I said, I'm going to talk a bit about the second type of clouds, and those are ice clouds. So the clouds that we talked about, they consist of droplets, whereas the clouds I'm going to talk about now are consisting of the ice crystals. And for example, in the Arctic, those ice crystals form within tiny, tiny sulfate droplets. So you get ice clouds which are pretty dense. And because they're so dense, they have a very strong long wave radiation effect, which means they keep a lot of, or they reflect a lot of thermal radiation back to our surface. And this means of all those very high ice clouds have a warming effect. So the hypothesis of ice cloud thinning is now, if we could remove those clouds, we could also potentially remove that warming effect, which then effectively would be a cooling. So how would we do that? So as I said, ice clouds form on tiny particles. So the idea is really to add steam aerosol to ice clouds and thus impact the balance between different freezing processes that occur in ice clouds, so that effectively those clouds would have a shorter lifetime because you have large ice crystals growing, and those would sediment out, which leads to thinner clouds and thus less warming. But as I said, if marine cloud brightening is very complex, this takes it to a whole nother level, because freezing processes are not as well understood as the formation of cloud droplets. So this is an even greater challenge, I'd say, than marine cloud brightening. And what is also possible is that if we not impact the diffusing processes in the right way, we could also create denser clouds or clouds in other areas which didn't have ice clouds before. And since those have a warming effect, we would create additional warming effect. So that's a very great danger of this kind of climate engineering approach. So just summing up, what I really want to highlight here is that research on radiation management is very, very complex and has from atmospheric sciences to physics over engineering and then also to economics. And what is really at the key of the physical sciences understanding of cloud-based radiation management is really the question, how well do we understand cloud formation on a global basis, and how can we improve that understanding? And then obviously there's lots of other questions which fall in different areas of physical sciences and engineering and economics. So that's just what I wanted to share for today. Thank you.
That was a really, really good overview. And I like what you said about the ice clouds, because, and I think William might be talking a little bit more about ice clouds later on, because they seem to be really quite difficult to understand and very important to the energy balance in the climate. So look, let's move on. And Rebecca is here. Rebecca has come up from London this morning. Now, if you plug that into there, I think you might find. So, and if I go to Lectern laptop.
Oh, yes.
And then climate repair, that looks like it. I've done Lectern laptop, is that right? Oh, Lectern PC.
Brilliant. Okay.
So excuse me, because I don't know you that well. So can you introduce yourself?
Yes, of course.
That's really bad.
No, that's fine. Hi, everyone. My name's Rebecca. I'm a final year PhD student at the Space and Atmospheric Physics Group at Imperial. I work with Ed Grisbeert, who you may or may not know, but he, we work on largely aerosol cloud interactions, and I particularly focus in the Arctic. I don't normally do stuff with, I'm not particularly familiar with the marine cloud brightening community, so thank you very much for having me. But obviously my research does lend quite nicely into the kind of stuff you're looking at, so I'm happy to present it. So today, obviously, Isabelle gave a very nice introduction to ice clouds and generally the idea of marine cloud brightening, but I'm going to focus a little bit more on liquid clouds and how aerosols affect their properties, and also in particular, how that might change with warming, which is obviously quite pertinent to the Arctic. So obviously we did have a bit of an introduction to cloud physics, but I'll go through it again just to make sure we're all on the same page. Obviously, if you, one of the kind of most famous or most well-known effects of aerosols and clouds is so-called the Toomey effect, and you're all probably familiar because this is the basis of marine cloud brightening, but it's the idea that you take an unperturbed cloud, you inject aerosols, you end up getting a larger number of droplets, and those droplets are smaller, and that overall increases the albedo of the cloud, which results in a cooling effect. However, the cloud may change further with those aerosols. So one effect could be that, those smaller droplets form precipitation less readily. This precipitation suppression mechanism, also known as the kind of cloud lifetime effect, increases the amount of water held by the cloud, so which is known as the liquid water path. That in turn increases the albedo and is another cooling effect. Now these, as we heard earlier, these smaller droplets may evaporate more readily. That evaporation essentially causes mixing in of dry air at the top of the cloud. That leads to further evaporation, loss of water in the cloud, and that in itself is a warming effect. Now in terms of the climate, the Toomey effect is relatively well understood. There is still some uncertainty about the radiative forcing of maybe half a watt. But what is particularly of interest to me are the so-called adjustments. There's a lot of uncertainty about them. They're very difficult to study. They're very difficult to get correct in models. And obviously for something like marine cloud brightening, knowing how these effects work and whether or not they're enhancing or offsetting the Toomey effect is going to be quite crucial, even in terms of thinking about the scale at which you might need to do marine cloud brightening to get a certain effect. Now, in terms of my research, I use satellites to look at these aerosol cloud interactions, or is specifically looking at the liquid water path response to changes in aerosol. Aerosol, you may know, is very difficult to measure in the Arctic, so I actually look at the droplet number, liquid water path relationship. And that makes sense because we pretty much know that an increase in aerosol gives you more cloud droplets. So you can kind of think of droplet number concentration as a proxy. Satellites are obviously quite useful as well because it gives you quite a large scale to look at these effects. And this map here shows basically the change in liquid water path for a change in droplet number concentration. And the blue areas on the map is when you get a decrease in liquid water path for an increase in aerosol or droplet number concentration, which in effect offsets the Toomey effect, which obviously isn't great. But the red in the map shows where you do get an increase in the droplet number concentration. So an enhancement of the albedo, enhancement of the cooling effect. Now this map, while it is useful, it does hide a lot of the nuance. So for example, it assumes this relationship is linear when we know it's not. It does change at very clean conditions to more polluted. But also this doesn't really take into account meteorology, which we know really affects the form of this relationship. And for this talk, I'm going to focus on one aspect of meteorology, which is what is known as the lower tropospheric stability. It's essentially measuring the temperature difference between a level in the atmosphere and the surface. And you can think of it as kind of like the amount of mixing, I suppose, in the boundary there. But it's particularly interesting to us because this is dominated by surface temperatures in the Arctic. And obviously, surface temperature is changing quite a lot. And also, this map here, amongst other studies, shows, although it's not super clear, just the way it's projected, but essentially you can see there's going to be a decrease in stability in the Arctic in the future because of this warming. So knowing how those aerosol cloud interactions may change with this is obviously key. So with all that said, this is a different way of looking at the the liquid water path response to droplet number concentration, as a function of high stability conditions, so less mixing, and then low stability, so on the left and right. And it's obviously as a function of the droplet number concentration. And essentially, if I walk you through, I don't know if people can see this very well, but if you look at the high stability conditions, for right up until actually quite high or relatively high droplet number concentrations, you persistently get an increase in the liquid water path. And that obviously is good because that's a cooling effect. And I won't go into the full mechanisms of why this is happening, but this is from a paper I published last year. So if you are interested in why that's happening, I recommend having a look at that. But essentially, in contrast to this effect of high stability, you can see in low stability conditions, while initially when in very clean environments where you have low aerosol, increasing the aerosol amount to a certain amount gives you a cooling effect. But actually beyond that, it's this negative slope basically gives you a warming effect. So to reiterate, increase in liquid water path with droplet number concentration in high stability conditions gives you a cooling effect, but in lower or more unstable environments, you get a warming effect. What of most interest to us is the fact that you can use these lines essentially to do some calculations to figure out the degree to which this affects the Toomey effect. And these green circles here show basically where the bulk of the droplet number concentration distribution in the Arctic is. So it's using the slopes of the lines kind of around here. And what you can see is that, it's not very steep, the slope, but in these high stability conditions, you do get a slight enhancement of the Toomey effect, so stronger brightening for an increase in aerosol. But quite worryingly, in these low stability conditions, which we are heading to more frequently in the Arctic, you actually do get a reasonably significant offset of the Toomey effect. Oh, sorry, extra slide. So that was quite a quick run through of some results, but essentially, warmer Arctic may lead to more unstable conditions, which for marine cloud brightening may eventually mean that you get essentially less effective marine cloud brightening. But also what is, I think, important to note here is that this effect, this kind of temperature-dependent aerosol effect, isn't necessarily seen in subtropical clouds because you don't get the same high stability conditions. So if you're looking to see analogs to estimate the effects of marine cloud brightening, these subtropical stratocumulus aren't necessarily a good analog for that. So that was very quick. But thank you for listening.
Well, thank you very much. I've got a question, which I guess is, can we kind of use our understanding of clouds in this way, perhaps to decide, oh, well, today is not a very good day to do marine cloud brightening. Let's wait until tomorrow, or let's do it next month, or gee, we should have done it last month. I mean, how much can we adapt our daily, if we do get into marine cloud brightening, can we adapt what we do based on what the clouds look like?
I'd say that's obviously quite a tricky condition because You'd have to be able to measure, I suppose, things like the environmental stability amongst, I haven't put in here, but the above cloud humidity also can affect not necessarily the form in terms of the positive or negative relationship, but like maybe the steepness of that slope. So you would have to have some good way of measuring, I imagine, over relatively large areas. There are some seasonal effects. So for example, during the summer, which is good for the, obviously we care about this in polar day, you tend to have much more stable environments. So you can have kind of an a priori guess that, okay, this month might be better than some other time. But I think, yeah, it would be I'm not sure, maybe more people know about measuring weather conditions in the Arctic, but it seems like quite a difficult thing to do.
So I've got a question.
I'll shout it.
No, because it's online. So, yeah, put people online. So we do need to use the microphone.
I'm Alan Gadian, Leeds. The question I've got is, I've done some work with Ian Brooks, and the importance of the inversion. You haven't mentioned the inversion in the marine boundary layer in the Arctic. It is varying. And have you considered, or do you have any comments on how this might change in a warmer climate, or how it affects your results? It's particularly the inversion.
Yeah, so it's a good point. And essentially, I didn't necessarily go into it, but one of the reasons that you get this form of the relationships with this positive slope, I think a stronger inversion is going to give you a more positive slope because it's more difficult to mix in the dry air. So yes, I had to select a small subset of results, but that is obviously very important. So stronger inversion, I think, I can't remember exactly how we expect the inversion to change in the future, but as you said, it is very important to think about, because basically this positive relationship you would expect there is because there's not as much mixing in or evaporation and treatment, so decreasing the liquid water path.
Hello. So the warming and cooling you showed, like with those plots, is that just from like reflecting shortwave, or because doesn't increasing liquid water, isn't that also going to increase the amount of infrared that's blocked? So that would be a warming as well.
The cooling effect of clouds in the Arctic is much stronger than any warming effect during polar day, and it's partially because the emissivity of clouds essentially plateaus after about 30 grams per meter squared for liquid water path, and the vast majority of clouds in the Arctic are above 30 grams per meter squared. So even if you increase the liquid water path further, it doesn't really affect the emissivity.
All right, thank you.
So at the very low liquid water path, it would.
Hi. It seems from what you said that the window of opportunity for cooling using this technique in the Arctic is actually narrowing, if anything, because of the increase in instability of conditions. I know Stephen Salter is he's suggested that the best way to cool the Arctic using marine cloud brightening is actually in the tropics. So actually from outside the area, cooling the oceans, because he said it was all the heat moves towards the poles eventually. So to basically step out of the box, the Arctic, to cool the Arctic. What do you think of that? Obviously, there's more liquid clouds around, or potentially other techniques. I know you're looking into different variations on this, but what do you think of that? Actually, stepping out of the Arctic and even out of the subarctic to cool the Arctic.
I will confess I'm not an expert in those kind of dynamics, so I don't know a huge amount of the kind of the way that kind of large scale energy transport would occur. But I suppose if the key is cooling the ocean, then I suppose any kind of ocean currents moving north, getting those cooler as well. I think, is that what you're trying to discuss?
That's a very good fertile area for discussion. We can talk more about that later on. Yeah. Perfect. One last question and then we'll move on.
Yeah. Hi. You're saying that if you have these unstable clouds, then you don't get a warming, you don't get a cooling effect when you add the droplets. But my question is twofold. Firstly, I want to understand, can you reliably tell the difference between these clouds? And do the droplets hang around long enough that they might end up affecting one type of cloud and then later affecting the type of cloud you don't want? I mean, like, how controllable is the overall system? Is this a fundamental problem for the process, or is it just a case of having to be a bit more careful?
I think this feeds into what you asked earlier in terms of being able to tell the meteorological conditions on the day, which again, I'm not necessarily an expert in. So being able to tell, you know, the stable versus unstable conditions, which is what affects the clouds. I really don't know how well, because I use reanalysis data, so I'm looking at data from years ago. So I'm not quite sure how well you can tell. I guess that's something that needs to be considered if you want to do something like marine cloud brightening. But the clouds can be very persistent in the Arctic. So maybe it is a case that I don't know how quickly the weather conditions change though. So I'm not sure you'd necessarily go from a very stable to a very unstable environment quick enough for your marine cloud brightening to have shifted to one cloud time to another.
Great, thank you very much. Big round of applause for Rebecca. Edmund Reardon is doing his PhD, started in January. Spent 10 or 12 years after doing his astrophysics degree in Brighton, working in the construction, kind of sustainable construction. What's the best way to describe it?
Yeah, sustainable construction.
There we go.
Joinery. Yeah.
And then decided that actually there was work that needed to be done on marine cloud brightening, and he's going to tell us where he's got to in a few months of his PhD and masters.
Okay, thanks for having me. Yes, so my interest is in the practical design and build of the actual sprayers for cloud brightening. And that's what I've been working on for the last few months in this PhD, which followed on from a master's project, which was a few months long before, also in Cambridge. So I'll tell you briefly about the droplet generation requirements, and then I'll tell you about the experiment I'm doing in this development. So just briefly, people have told you about what cloud brightening is, but just to point out, it is spraying seawater from the surface in a fine mist is the main basis of it, where the salt crystals evaporate and go into the clouds and cause the whitening. So these might be sprayed from automated vessels that are driving around, like Stephen Salter's designs, or they might be sprayed from wind turbines. But really the first hurdle is to get the nozzle spraying the right size droplets. These are the sprayers that Dan Harrison has been using out on the Great Barrier Reef on his field trials there. He's probably the furthest down the line with it from that point of view. But yeah, my interest is in the actual sprayers inside those adapted snow cannons. So the requirements are you need a droplet that is being sprayed somewhere between 200 and 800 nanometers, depending on which papers or modeling you're looking at. There's an agreement you need a narrow size distribution, and you need to spray somewhere above 10 to the 15 droplets per second per spray source or per vessel. So the spray mechanisms that are being used, I'm not going to tell you much about these because other people here are working on these, but really they fall into these two categories, which are one where you have a single nozzle is sending out a single stream of droplets. So that's like Stephen Salter's Riley jet breakup and the electro spray, but Jake is going to tell you about those shortly. The other type is a ballistic breakup, where you have multiple streams of droplets coming from one nozzle, and that is the effervescent spray which was developed by Armand Newcomans and his group in California over the last 15 or 20 years, and what is being used on those snow cannons by Dan Harrison. Another form of ballistic type breakup is superheated atomization. That is the area that I'm looking at. So that is multiple nozzle droplet streams coming from a single nozzle with a large orifice, and you basically have a situation where you're heating up your fluid, your seawater in the pipe to above 100 degrees. Here it's held under pressure and it can't boil. So as it's coming down the constricting part of the nozzle, you have an acceleration of the fluid and nucleation sites. The pressure is dropping because it's accelerating, and these nucleation sites, these bubbles are growing. And then when they reach atmospheric pressure at the edge of the nozzle, the opening of the nozzle, you have a rapid expansion, and that is blasting apart the film of liquid around them, which breaks up into these droplets. And it's those droplets that I'm hoping to find if they can be in the correct range for MCB. So superheated atomization is used in many different applications. You have fuel atomization in fuel injection. So I've looked at lots of this. There's a few studies that show you're getting down close to the 1 micron size range in that. There's this, so this size distribution is from some Russian papers, which I believe Dan Harrison came across these first, and I was put onto these by Armand Newcomen's, but they are showing cooling gas turbines by spraying in fresh water, and they're using superheated atomization to create the droplets for that cooling. And they're representing this size distribution, which is appealing to MCB because you have this 90% of the size under 1 micron. They're actually talking about radius here, but it's in the correct ballpark, and it suggests useful applications because it's a scalable technology, the nozzles for this, and it is suggests, although you have a high energy requirement for heating fluid up to these 200 degrees, you have a large proportion in the correct range. So it's the efficiency of the number of droplets you're creating in the MCB range that's important. So other literature on superheated atomization is talking about a potential narrowing of the size distribution when you're spraying at higher temperatures. It's widely reported that reducing the nozzle size and increasing temperature and pressure is going to reduce the droplet size. But basically these papers that represent this are all, they don't appear that reliable, and there's a certain lack in the data there. And so it's this kind of size distribution I want to see if I was able to replicate. And so I wanted to develop an experiment looking at the same parameters that they were looking at in those. So that's trying to achieve 204 degree water spraying at 74 milliliters per second. This requires a high energy requirement, 58 kilowatts, or to have a continuous flow, or you need to heat up a large vessel of water, and both of these are not were not ideas that were received very well as an MPhil project in the engineering department, because it's too larger operation. But so I reduced the nozzle size right down and reduced the flow rate right down. And so now I've developed an experiment which is just using 1 kilowatt of power. But it does mean that you've had to scale everything down in the nozzle to achieve that. And this is really to investigate the claims that they're presenting in those papers. So this is what the basic design was. You've got a pump here that's driving water through these heaters, taking it up to superheated temperatures and atomizing here at the nozzle, and then it's being observed in the duct here with this detector and with imagery. And everything else here is related to safety elements. You've got pressure relief valves and check valves and filters, and pressure and temperature sensing happening. And so this is basically what that looked like when it came. This is the new laboratory that we've developed. There's mine and Jacob's experiments in there, but you've got the sprayer here spraying into a clear duct that you can't see here and being extracted out here, and this is the particle detector, and you've got the power supplies shielded off here. So just this was what the setup looked like a couple of months ago. And just as very initial just to get an initial idea of what was going on. Once that was set up, spraying seawater or lower salinity than seawater, I just took a few samples that were collected on little metal stubs and then put them under a microscope to observe. And there's some salt crystals which had encouraging sizes there. There's a scale down here, but this is just taking observations with a microscope. This is not getting a proper statistical analysis of the size distribution. That really comes with the particle detector. These were taken at lower salinity than salt water, because you have, this is what the nozzle looks like after 10 or 15 minutes of spraying with 3.5% saline, which is salt water. So it breaks down all of the seals in swage lock fittings and causes this build-up, hence using the lower saline solution. This is just a video of the sprayer running. So this has reached superheated atomization. You can see it spluttering there. That's where you're getting choked flow occurring, where you're starting to have bubbling up and boiling is happening in the nozzle and reducing the flow. That's an issue because you can have a situation where the whole system can block because you've had a boiling up happening inside the pipe. And this is what so this is the water pipe I had to cut into after it is completely blocked. And you've got this, you can see this is the salt that's been deposited inside there. So these are just some of the issues I've been coming across when I've been developing it. Anyway, so that was building the sprayer. That's all operating at superheated temperatures, but really the difficult part comes when you're trying to detect the salt crystals downstream of the nozzle. And that's really everything that I'm working on now. So in detection, you can either look at the spray directly here with a look at the laser Doppler and measure the size of the droplets, or you can do what I'm trying to do here, which is where you're drawing in droplets and drying them out and taking them into your particle detector. But it is knowing that you are what your particle detector is showing you is what is actually being measured here, and there's difficulties of losses happening in all of this process. So that's what the diffusion dryer looked like that I built, and the our technician put this together. These are the aerosol is split into three here, and it's sent down these tubes, and it is dried out into silica beads. This is all full of silica beads. This is what the lab is looking like now. It's been raised up, and this is that setup diagram in this is a duct here, but rotated to vertical so that you have your aerosol passing down through your dryer, so you're not dealing with so you're reducing your gravitational losses, and it's coming out of the dryer here and into the particle detector. So really this is all what I'm working on now. And I'll just point out there's a visit to the laboratory as well. So I'm not going into too much detail here because you can all come and see this in person. Lastly, the other bit I'm developing is the nozzle. And so this is the scaled down version of the nozzle that was in those Russian papers, trying to achieve 0.1 or 0.2 mil orifice here is quite a challenge. So in conclusion, I've just given you an outline of what the requirements are of the sprayer, and there are some suggestions that superheating offers potential in other applications. You can see that they're getting down close to it, and really that's the experiment I want to develop to show whether or not this is going to be achievable in that range. Okay, and that is all of my presentation. I'll just briefly say that the reason I got into cloud brightening a few years ago and why it really appealed to me is that it had the local nature of it and the short-term nature of it. Really, just from talking to other non-academics about this, and over the last few years, I think this is really, that's why this is going to be something that can potentially be accepted by people and something that could potentially be used. And it's going to be possible to do field trials in this. And it's really that appealed to me. Out of all of the different cooling techniques, this seems like one that could be a goer from that point of view. And that's really why I left what I was doing a few years ago and completely committed to developing this. Okay, thank you.
Questions for
Edmund, that's a very, very interesting. I'm Robert Chris, an independent researcher and associate of climate repair. Edmund, great presentation. Just one question: Have you done any work to assess the energy requirement were this idea to be scaled to something that was climatically significant?
Yes, so the basis of it is the enthalpy in raising the water to whatever temperature. If you were gonna, so if you based it on that size distribution which was displayed in the Russian work, you could be looking at a few kilowatts to produce 10 to the 15 droplets per second if you could achieve that 90% down in the MCB range, and if you use the 200 odd degrees that they were using. Question is that size distribution reliable and can that be achieved? So I suppose the only comparison you have is the pneumatic energy requirements of the effervescent spray that's being used on Armand Newcomen's nozzles and on Dan Harrison's at the moment. And that size distribution from the Russian work suggests that you would have a more appreciable energy requirements. But to be honest, for now, I think the only thing that needs to be done is we need to develop field trials which are going to be able to observe the effects on the clouds, and for that the energy requirements don't matter, but we need to by any means possible get droplets generated at the right rate in the right size. Obviously for scaling up, energy requirements are essential, that's the key. So this may or may not be the one for that, but for now the only thing that my focus is on trying to get droplets into the right size range that can be scaled up enough to do field trials and observe the effect. So yes, I have thought about the energy requirements is the answer.
Well, I think on the energy front, the compressing air and then expanding it is it's an inefficient way of producing the droplets. So the effervescent sprays are at the moment using a lot of energy. But the advantage, I think, in your technique, Edmund, is that you're compressing water, which you can do quite efficiently, and so there's a lot of potential for that to be achievable. We've got some questions online, which are Brian von Hertzen. Well, okay, no, I'm just going to, okay, there are some for different talks. You know what, I'm going to come to some of the questions online for the general discussion because I think they are, okay, we'll come back to them because they're more general about the thing. But we haven't forgotten about the questions online, so please keep them coming. I've got some from Brian von Hertzen, from John McDonald, which is great. So we'll come back to those. We've got a question from Andrea about, then we'll move on to.
So I understand that you're imagining this as a flow process, right? So it's continually done in situ. But an alternative, because you described that desiccation step, which I admit I don't fully understand, is it not possible that you could centralize this and use a process which leads to bulk manufacture? So you're just taking tankers of desiccated salt particles out to boats and then distributing them with boats or maybe even aircraft in the field, because most of the energy requirements you're talking about are within the range of what you could get from waste heat, right? So if you've got a nuclear power station, or you've got a steel mill, you've got waste heat, which is close to 200 degrees, right? So if you could centralize this process and deliver bulk particles, it's going to slash your energy requirements and massively increase your process robustness.
Yeah, okay, so I did, when I was first looking at cloud brightening, I did look at developing, so you're talking about just producing solid particles, taking them out and then spraying those. Is that right? Yeah, so the difficulty you have there is that they agglomerate together, and you don't, the easiest way to produce consistent small solid particles is by evaporating them from a spray. And the methods I looked at, because there's much simpler methods for crushing up solid particles into small particles. You can use just ball milling is a process I looked into quite a lot. But the difficulty is that you have a very wide range of size distributions because of the agglomeration. And so that is why people use things like nano spray drying to, even though they're just trying to produce single small solid particles, the only way you can do it is by evaporating them from the fluid. Does that answer your okay.
We've got one last question.
Hi, yeah, it's on scaling up, but so, hi, I'm Daniel Key. I'm a former Imperial MSc student, but I'm now doing marketing, but I'm here skiving work for the day, probably get sacked. Anyway, no, I was going to say when you showed us the fouled up, or snarled up nozzle after 15 minutes with a certain concentration of salt water, with the concentration, I think you said 3%.
Yeah, 3.5%.
Right. And then you showed obviously the other nozzle, which was much lower concentration, not fouling up. Have you worked out, is there a critical concentration of salt within the water?
No, it's just been, I've just had less problems when I'm spraying 0.5% as 3.5%. No, I haven't categorized that precisely, but yeah, it's just easy. And also, I didn't say there, but I'm running through just the pump is actually just a cheap pressure washer from B&Q, and they're not really designed to have hot salt water flowing through them. So yeah, it's still surviving though. It's lasted a few months already.
And for the Australian audience, B&Q is fine. Right, thank you very much, Edmund.
Good.
Right, so William McFarlane-Smith is in the second year of his PhD. He's working on a combination of marine cloud brightening and cirrus cloud thinning. William, over to you.
Yeah, okay. So I mentioned a bit about marine cloud brightening again, but mostly I will talk about cirrus cloud thinning. I assume most people are familiar with GeoMIT, but it's the geoengineering modeling into comparison project. So looking at doing kind of the same geoengineering experiment, but in lots of different models to compare the results. So basically cirrus cloud thinning was run. There was a cirrus cloud thinning running that, which I will be talking about the results from here. So I'll start just by introducing the idea of cirrus cloud thinning, which I think most people already touched on, so that won't take very long. I explain the G7 cirrus experimental design, and we'll just look at some results so far and some conclusions. So I think everyone's already kind of spoken about this already. Clouds have a warming effect and a cooling effect. Cirrus cloud thinning is exploiting this warming effect by thinning high up cirrus clouds, meaning that they trap less infrared heat. So that has a cooling effect on the climate. And yeah, so it's basically you take clouds, so you want clouds that are freezing homogeneously, so about -40. So whether or not a cloud forms like a liquid cloud becomes an ice cloud, it depends. So if it's below 0, it depends if it contains ice nucleating particles, but if it's below -40, then it will freeze homogeneously, so the water will just freeze straight into ice without needing any nucleation. But that's quite a slow process. So if you have clouds in those conditions and introduce ice nucleated particles, you'll accelerate the freezing rate. And this will make the ice crystals bigger. And that will, I just realized what I'm explaining is on the next slide, actually. So yeah, so this is the idea of cirrus cloud thinning and then how it works. So you have water at -40, which freezes homogeneously. You add the ice nucleating particles. They cause heterogeneous nucleation, which becomes which is faster and becomes the dominant process. And then the ice crystals grow more rapidly. Larger ice crystals fall more quickly, so they're heavier, obviously, so they're going to fall quicker, and that thins the cloud. And then more outgoing long-wave radiation can escape into space, which cools the climate. So, yeah, that's the idea of cirrus cloud thinning. And then in GeoMIP, so say the Geoengineering Model Comparison Project, so it was run, and cirrus cloud thinning is often kind of neglected, which is shown by the fact that this experiment was run in 2015 and no one has analyzed the data yet. So that's what I'm doing. So yeah, it's called G7 Cirrus. They wanted to do it in as simple as way as possible, so as many models could do it. So the way it emulates cirrus cloud thinning is just by increasing the fall speed of ice. So this is all global climate models, so their representation of aerosol is like all parameterized and the clouds are parameterized. So it's like a highly idealized way of representing it, just so that as many models can do it as possible. And it calls an SSP 585 scenario, by increasing the full speed of the ice crystals. So far only 2 models have run it, and that's UKESM1 and IPSL. And so you've got blue is UKSM1, the dotted lines are the SSP 585 scenario that we're calling, and then the solid lines are G7 Cirrus, like the key tells you. And you can see that just from this, like it does do some cooling, more so in UKSM1 than IPSL. And so far, these are the only 2 models that have run it, but there are GIS is also going to run it, and maybe CESM. Just now that I'm analyzing it, more people are interested in doing it. So yeah, this is a change in annual mean. So this is near surface atmospheric temperature, and like the baseline is pre-industrial. And if we look at that on a map, so this is just taken from UKSM1, you can see that most of the cooling is in the Arctic, although we'll see almost the temperature cooling is in the Arctic. We'll see radiative forcing later, and it's much more effective. Well, it's more effective in UKSM1, so you get a total cooling for the end of the century of -1.24 Kelvin, whereas IPSL is only -0.5 degree. So yeah, IPSL looks like this, but it's just paler. And then this is atmospheric temperature, but like seen vertically. So this is your pressure levels, this is latitude, that's not labeled. And you can see that generally there's cooling in the troposphere, with the biggest cooling at the top of the troposphere, but you also get this warming in the stratosphere, which makes sense because if you're thinning the cirrus cloud, more infrared radiation is getting to the stratosphere, so that will be heated compared to the baseline scenario of SSP 585. And then we can also look at radiative forcing. So this one is a bit messy because it's all close together, but you've got roughly your asset, both the SSPs are in there, so the dotted lines, and then you can see that there isn't a lot of radiative cooling in IPSL, so it's more or less on top of it. It's slightly below it, but it's not very significant. But then there's quite considerably more in UKSM1 because it's visibly kind of come away from the ensemble members up there. And then we can look at this kind of latitudinally as well. So this is just cloud forcing, and we're looking at shortwave here. So like this is the sum of like shortwave going in or shortwave going in minus shortwave going out. And then this is like escaping longwave radiation. So you've got that like as we kind of saw from the other plots, that UKSM1 cools a lot more, and mostly you'll see that most cooling is in the troposphere. There's actually very little.
there's some in the Arctic, but the biggest amount is in the not troposphere, the tropics, like around the equator. But yeah, there is cooling in the Arctic, but if you remember from the temperature plot, most of the biggest temperature difference was in the Arctic. So there's clearly a lot of kind of Arctic amplification increasing this. And then there's like shortwave doesn't change that much as you'd expect. And then yeah, long wave isn't hugely different in IPSL. So definitely UKSM1 responds a lot more to it than it does. And then, sorry, I only just added those, they're not very obvious, but yeah, then it's about double the radiative forcing in IPSL in UKSM1 compared to IPSL. But then there are some quite big differences between the models. So this is like vertically integrated cloud liquid water, so like liquid water pathway. And you can see that just the trends are just completely different. Like in IPSL, it goes up, and UKSM1, it goes down. But this isn't just because of G7 Cirrus. Like you'll see both the IPS, both the SSP 585 scenarios are doing it as well. So this is just kind of highlighting the differences between the models, and that like doing clouds aren't very well represented in global climate models basically. And this is mostly because when the climate models are kind of set against the radiative forcing that the clouds do, rather than the cloud properties like this, like the liquid water content. And it's a similar story for like ice content as well. And then another big difference is the change in cloud fraction due to cirrus cloud thinning. So IPSL is kind of what you'd expect. Like there's a decrease, like this brown shows a decrease in clouds, and it's around about where cirrus clouds are, kind of up in the high troposphere. But then UKSM1, you get this decrease here, like in the tropics, as you'd expect. But then you also get this big increase in like polar stratospheric clouds, which is, I don't know, interesting. I don't know why. Need to figure out why still. And then it'll be interesting because this is obviously, if you're comparing two models, like they can't both be right. Neither of them might be right. You don't know. But we need so that's why it's good that it's now being run in a couple of other models. So cool. So conclusions so far. So CCT does cause negative radiative forcing, and Arctic amplification plays an important role. But I think the kind of point of this study is more going to be to highlight the differences in how global climate models represent cirrus clouds, and understanding them better and how they can be represented better, rather than actually telling you much about whether or not cirrus cloud thinning is a valid form of geoengineering, because it's just hard to tell from these models, because this is, like I say, it's a very idealized representation of it. And then future work, so I'm also doing some work on marine cloud brightening, and it'll be interesting so I'm doing that in like an LAS simulation. It'll be interesting to look at cirrus cloud thinning in that as well, just kind of to get an understanding of the aerosol particle and aerosol cloud interactions. Because there's still some question marks about how effective the actual microphysics of cirrus cloud thinning is, if it actually works. And then also maybe looking at cirrus cloud thinning in the Arctic, because a lot of, as I think has been touched on a bit, a lot of kind of when SRM is just focused on the Arctic, it often isn't as effective as you'd like it to be. So maybe if looking at modifying outgoing long wave radiation rather than incoming shortwave could have different effects. And then, yeah, I thought I'd mention I'm also doing some work on marine cloud brightening in Monk, in case anyone wants to talk about that, but I don't really have any results to present on that. Cool, thank you.
Right, yeah, questions for William, and we've been asked by the online audience to speak directly into these microphones.
Thank you. Very nice talk, Will. There's 2 points. One is that you're very right to question the microphysics processes in these high-level clouds.
Yeah. And
the UK handling center model has some limitations, but so do all of them.
Yeah.
But so as long as you do appreciate that, that's the first thing. Good. And the second point is your cooling. It clearly demonstrates what was just mentioned here earlier, that cooling is most rapid at the poles. So if you want to cool the Arctic, the best way is to cool the subtropics or the flood. And I think that is a very valid point, and a major point.
Yeah, definitely.
So other side of the room, this is where I get some exercise.
This is Shaun Fitzgerald for those online. William, thank you ever so much indeed. The significant differences between those two models. I mean, what can we infer? Therefore, I mean, is it, are two models enough, or do we need to look at more models? But given that they're so disparate in terms of the way that they seem to be characterizing some of the physics.
Yeah, so that's what I sort of mean. It's kind of a way of like looking at these experiments in these different models is more useful for understanding the models than the real world, really, like in terms of how they are representing cirrus clouds and how we can then improve our representation of cirrus clouds in them. Because like cirrus clouds are probably the worst represented, like clouds are poorly represented, and cirrus clouds even worse than regular clouds in global climate models. So it's this, like I said, this is more about that. This is going to be, I think this study is going to be more about that than telling you whether or not cirrus cloud thinning is an effective means of geoengineering.
Isn't that what GeoMIP is all about?
Yeah,
because
exactly.
It's about comparing the models and finding out where they're different and why they're different.
Yeah,
so
exactly.
In a way, the fact that they're different is to be expected.
Yeah, exactly. Yeah, they've all been designed with different parameterizations and that sort of thing. So,
right. Well, thank you very much, William.
It's okay.
And scheduled speakers for this morning is Jake Chapman, and Jake has just finished yesterday his master's. Has just finished yesterday his master's thesis, and the presentation he's going to give now is what he gave yesterday. And great. And Jake is planning to do a PhD on all this stuff starting in October. So this is a good dry run for all that work. Over to you, Jake.
Cool, thank you. So hi everyone. I'm Jake, and as Hugh mentions, I just finished my master's. And part of my master's was to undertake a project with the Centre for Climate Repair, in which, similarly to Edmund, I was focusing on different methods of generating droplets for marine cloud brightening. As Edmund has already mentioned, there are a few desired properties of the spray that we wish to generate for marine cloud brightening, and that throws up a lot of significant engineering challenges regarding the spray generation hardware. So as Edmund has mentioned, we need the droplets of seawater to be very small, ideally submicron. We want the spray to be as highly monodispersed as possible, so this is where all the droplets are the same size. We need to generate a lot of droplets per spraying device, and because these devices are going to be out at sea for long periods of time, we ideally want to keep any power consumption to be as low as possible. There are also issues with clogging and making sure that the devices that we develop can withstand continuous operation in the harsh marine environment. So my project has been focusing on two different spray generation methods and investigating their suitability for marine cloud brightening. The first being electrospraying, and the second something called the Riley jet method. So firstly, electrospraying. So electrospraying involves establishing a high electric field at the tip of a capillary filled with the liquid that you wish to spray. Opposite the capillary will be a grounded or negative electrode, and the capillary itself will be the positive electrode and will charge the liquid. In this case, it will be seawater. Now, the behavior of an electrospray is particularly sensitive to the applied voltage and flow rate, but it's also influenced by the electrode arrangement and the properties of the liquid that we wish to spray. For marine cloud brightening, we ideally want to operate in something called the cone jet mode. So this is where the liquid leaves the capillary first as something called a Taylor cone. And then at the apex of that cone, a very narrow jet forms, which then disintegrates into a highly monodispersed spray. Unfortunately, electrospray behavior is particularly difficult to try and predict analytically, especially for really highly conductive liquids such as seawater. And there's been very little data in the literature on electrospraying experiments with salt water with salinities as high as that of seawater. And so at the beginning of this project, it wasn't particularly clear as to whether electrospraying seawater would even be possible. So my first aim was to really just try and do some experiments, electrospraying seawater or salt water at least, see what happens. Is a stable Taylor cone possible? And then moving on from that, can we optimize it to be suitable for marine cloud brightening? So to do so, I built a custom electrospray rig where the spray would be generated from the tip of a syringe needle. I was using water with a salinity of 3.5%, same found in seawater. And my first tests were just proof of concept tests to see whether a stable Taylor cone could actually form. And then I moved on to trying to map out the voltage ranges and flow rate ranges in which a stable cone jet mode could be achieved. I also attempted some measurements of the sizes of the salt particles being generated as well. So this is an example of what was typically observed. So this is for a fixed flow rate. We're looking at the syringe needle tip, and I'm just increasing the voltage from 9 to 10 kilovolts. And I have outlined the surface of the liquid coming out of the needle tip in red to make things a little bit clearer. And what we can see is that in a fairly narrow voltage range between 9.2 kilovolts and 9.6 kilovolts, we get a really prominent Taylor cone forming. But for lower voltages and higher voltages, we lose that cone jet mode. And we observe other modes, such as a dual jet mode, where the meniscus actually splits into two slightly smaller cones. This is particularly unstable, so often you get these two jets spinning around the tip of the needle. At really high voltages, we run into an issue known as corona discharge, which is where you get ionization of the air around the needle tip and you get a buildup of plasma, and it can lead to sparking, which isn't great. The main result, though, from these experiments was a fairly positive one, because it showed that electrospraying salt water with the same salinity as seawater is indeed possible. And I've plotted out the stable voltage and flow rate ranges for a variety of different electrode arrangements to understand what our working parameters will be, and also to see how they change in terms of scaling things down in terms of size. Unfortunately, my sizing attempts or sizing the particles, the salt particles generated, were largely unsuccessful. As Edmund mentioned, this is particularly difficult to do, and so it will require improvements to my setup and my sampling method. I already have some ideas in mind, and I'll be trying them out first thing for my PhD. So moving on to the second part of my project, which is concerned with generating droplets using a method known as the Rayleigh jet method. And the Rayleigh jet method is all based on this phenomenon known as plateau-Rayleigh instability, which is the reason why water jets, say coming out of nozzles in a shower head, such as this one, break up into droplets. And a really interesting effect of the plateau-Rayleigh instability is that the size of these droplets will be typically twice the diameter of the jet or twice the diameter of the nozzle. So therefore, if we want to, say, generate 1 micrometer diameter droplets of seawater, we need to pass that seawater through nozzles with a size of 500 nanometers. Now, this is incredibly small. Just put that into context, that's around 100 times smaller than the width of a human hair, or 10 times smaller than a human red blood cell. So how do you make these submicron nozzles? Well, one idea is to use semiconductor device fabrication techniques and try and etch these submicron features in a silicon wafer. And it's also been suggested that you can improve the uniformity of the droplets being generated by introducing a pressure perturbation to the flow as it exits the nozzle. And so the second half of my project was concerned with evaluating this concept in particular evaluating the fabrication requirements for making these submicron nozzles, and also doing some fluid simulations and COMSOL modeling to better understand how an induced pressure perturbation can improve droplet formation. So for my initial fabrication attempts, the nozzles I envisaged would be made from, you take a 4-inch diameter silicon wafer around 0.5 millimeter thick, through most of which I would etch millions of 50 micrometer diameter holes. Now I call these big holes because at the end of each would be an array of much smaller holes. These would be around 1 micrometer in diameter. Both the small and the big holes would be etched using a technique called deep reactive ion etching, DRIE. And after all my fabrication attempts, this is what I've made. And what we see here is the 4-inch silicon wafer with, you'll notice there are around 40 squares patterned onto the top of them. Each one of those squares is around 10 millimeters by 10 millimeters in size. Each one contains around 1 million nozzle holes. This is a closer look at those holes. So I experimented with different hole sizes and also hole spacings. So on the left, we have an array of 50 micrometer diameter holes, and on the right, a much more densely packed arrangement of 100 micrometer holes. The larger holes etched really, really well. For the smaller holes, this is an array of 1 micrometer diameter holes, and on the right, we have an array of 2 micrometer holes. And you'll notice that with these holes, they have more of a ringed appearance with these white dots in the middle. And it turned out that that's because they didn't etch as well as the larger holes. And actually what happened was there existed these short pillars of material at the center of each hole. And so that meant that they weren't etched fully. So as well as the fabrication side of things, I also did some COMSOL modeling of the Riley jet method through 3 different submicron nozzle designs that could be made using semiconductor device fabrication techniques. And the simulations were performed to better understand how the frequency and amplitude of a pressure perturbation, and also the operating pressure and nozzle geometry can affect droplet generation. And on the right, we have an example data set of one of the models through one of the nozzle geometries, and it shows the change in droplet formation for different excitation frequencies. So at the top, we have no induced pressure perturbation. At the bottom, we have pressure perturbation with an excitation frequency of 20 megahertz. And you'll notice that around in the middle, around 11 megahertz, we have a really nice uniform stream of droplets around 1 micrometer in size. And so these models just verified that an induced pressure pulsation will improve the uniformity of droplet breakup. And the models have allowed me to obtain estimates for the optimal excitation frequency, the optimal amplitude, and operating pressures for each of the different nozzle geometries. And I've also been able to obtain some estimates in terms of the power requirements and also the ease of fabrication for each of these 3 nozzle geometries. And a really interesting thing about this is that this method in particular can offer very, very reasonable power requirements. So actually, based on the hydraulic power alone, scaling up to 10 to the 17 droplets per second would require around 100 kilowatts, which is very reasonable. So in summary, for this method, the larger holes, 50 micrometer and 100 micrometer holes were etched very, very well. The smaller holes less so. But I believe that the issues regarding the unsuccessful nature of the unsuccessful etching of these smaller holes can be resolved fairly easily by just tweaking some of the parameters in my fabrication process, and everything is in place to try again. My COMSOL models have shown that an induced pressure perturbation does greatly improve the uniformity of droplet formation, and that the Riley jet method can offer very reasonable power demands, especially when scaling up for the scale required for marine cloud brightening. And that is all. Thank you.
Very good. Any questions for Jake? Yes, and do speak.
Thank you, Jack. My name is Hans van der Loo. On both the methods, did you run into any salt clogging like Edmund said? Because the holes, the edged holes are so small and the size of the salt particles in there, was that any issue with both methods?
So because the smaller holes didn't etch fully, I haven't actually passed salt water through the small holes yet. However, it will be a significant issue, especially when running at the same salinity as seawater. So it will require some serious filtration or some other method, maybe like a sort of a backflush method to clean out those holes. And yeah, that will be something, but that's another PhD in itself. So with the electrosprays, I didn't actually notice any clogging. Even having left it filled with salt water for, I actually left it filled with salt water for a few days. I came back to it and it wasn't clogged.
So how is, are we going to be able to see it running this afternoon? Are you able to come on?
Yeah.
5 o'clock-ish?
Yeah.
Is it like filled with salt water from your last use?
No, it's cleaned out.
Oh, very good. Okay, so we'll have a look at it this afternoon.
Jake, thank you ever so much indeed. Great. Could you just put into context, you mentioned 100 kilowatts. I couldn't remember the number of droplets per second that calculation was for, so let's say 100 kilowatts. And you also mentioned the effervescent spray being used at the moment, being quite energy hungry on the Great Barrier Reef project. Are you able to just let us know what that power requirement is and the difference between these two methods at the moment for the same droplet number per second?
Yeah, so for just scaling up based on these COMSOL models, it's around 100 kilowatts for 10 to the 17 droplets per second. I believe Daniel Harrison's current effervescent sprays are achieving something like 10 to the 12. And I think he's using 3 50 kilowatt compressors, so 150 kilowatts, so more power, much more power than this is a very, very efficient way of generating droplets. The trouble is actually making a working prototype is the difficult bit.
Hi, I'm interested at the interface between these two methods because you described them as being quite separate, but there seem to be quite obvious opportunities to integrate them. So your Taylor jet, in theory, you could fabricate a cone-shaped nozzle, and you could also use an electronic oscillator, not a physical oscillator, to introduce the Rayleigh jet instability if you charge the particles. So is there an opportunity to do that? And as a secondary question, when you presented these results here, you identified a mid-band where you get this quite stable flow of evenly sized droplets, but I don't recall you saying why that situation occurred. And if you could address that as a secondary question, that'd be great.
Yeah. So firstly, to answer your first question, yes, you can use clean room and semiconductor device fabrication techniques to etch very, very small needle-like structures, which would be your capillaries, and then you could use that for an electrospray. So MIT use electrosprays for satellite propulsion, but they've miniaturized it. And so they have an array of electrosprays around the same size of a 2p coin. So it could be that you could scale down everything in terms of, you could have an array of electrosprays working at a very small scale, and that could be fabricated using, say, silicon fabrication techniques like that. To answer your second question, the reason comes down to, so the Rayleigh, the plateau-Rayleigh instability comes from naturally occurring perturbations that occur on the jet as it leaves the nozzle. And some of these perturbations, certain frequencies and wavelengths grow faster than others. And there's a particular, that there will be one that grows the fastest, and it's that frequency that is the first one to cause droplet formation. So that 11.1 megahertz causing the best uniformity is because you're oscillating it at the right frequency.
Chamber harmonic effect.
Essentially, yes. So
We've
yes.
Got a question to William from Alice. And the question can you unmute yourself, Alice, and can we hear you directly?
Can you hear me?
Hello?
I'm not sure if that Antoinette is. Yeah, I think Antoinette is. But anyway, the question is, there seemed to be seasonal cycle in the IPSL global temperature. Is that something you can explain?
I think the result I was showing was annual means, so like I don't think that there shouldn't have been. But no, I've only looked at kind of annual stuff so far. I haven't like split it up into like a month by month thing is something that I still need to do. Oh, I don't know if I'll do it in this paper because this is just kind of preliminary results, but it's something that would be worth looking at, I think, yeah.
Okay, so we're entering into general. Thanks, big thank you to Jake. Now, so then we've got questions. Now, Antoinette, you've got the questions on your phone, so I can read them out. There are questions. Where are they? Right, let's work this out. So there's a question. Isabelle is still there. Yes, I think. Would ice cloud thinning also potentially work in the Antarctic, i.e. the size threshold between dissipation and brightening? Is that the right question? Now, I don't know whether we can. Isabelle's there. Isabelle's there. Can we hear it?
Yeah. Yeah. Can you hear me?
Yes, we can.
Okay, perfect. So we haven't really looked into that. And one of the things that is really tricky is cloud thinning in the Arctic or the Antarctic is the need to know the base state of the atmosphere, right? So that's something that that Rebecca has been alluding to. So we really need to know like how clouds form with a changing climate in order to know like how we can possibly intervene. So, and that is one of the most challenging things. And in the Arctic, we do have some more measurements to constrain, for example, model simulations. So that would be one of the advantages into first prioritizing Arctic cirrus cloud thinning.
And then we've got a question, and I'm not sure exactly who to, but yes, it may be also to you as well, Isabelle, about do you have a sense for the small scale salt particles that actually diminish clouds? So, you know, how small do you have to get before the particles make the clouds dissolve away?
So that's another really tricky question, but I'd say, you know, order of magnitude, maybe 100 nanometers, but with all the processes going on, so for example, the direct radiative effects, and then also the more complex feedback effects on the clouds, it's really something we need to investigate more and also based on measurements.
Great, thank you. So now questions from the room or from anyone want to? I mean, we're getting to the point where the people in the room, the online people have the advantage of being able to get up and stretch their legs whenever they like. The people in the room might like to get up and stretch their legs. Anybody who's so I don't know whether either Isabelle or Alice would like to make any comments on what they've heard since we can hear you. Oh, now we've got a list of questions on the screen. Well, I guess therefore, Edmund, have you looked at boiling salt water and then re-entraining salt spray back into the vapor stream to reintroduce particles for cloud condensation nuclei formation? That sounds like a higher level. But oh, we've gone small there. Can we get that back up again? Oh yes, so the question about the 100 nanometer there, Isabelle, is that 100 millimeter salt or 100 nanometer seawater? In other words, 100 nanometer seawater will give you 25 nanometers salt.
Yeah, so I was talking ballpark dry particles, but as I was saying, you know, it's a really tricky question. So definitely more simulations needed to fully answer that question.
Very good. I think we should take a break. I noticed that they have gone and provided us with nice coffee cups. So we can go and have a coffee, and we'll reconvene then at 11:45.
Ladies and gentlemen, we are going to reconvene, and we're going to go upstairs for the first part of this talk. And by that, I mean that we've been talking about marine cloud brightening, and we're going to go a bit higher. And we are going to be joined now by Alice Wells. Alice is a PhD student at the University of Exeter, working with Professor Jim Hayward, who is obviously at Exeter University, as well as very involved with the Met Office as well. And in fact, it was out of Jim's group that we were able to recruit William McFarlane Smith. So I don't want to suggest that it's just a very small community. We would like this community to be much, much bigger than it currently is, given the scale of the problems that we are set before us as mankind. But nevertheless, we are together today, and we're very pleased to be able to be joined by Alice. So Alice, the floor is yours.
Thank you. I'll just share my screen. Can everyone hear me okay?
Yes.
Oh, cool. Fab. Okay,
Yes.
So yes, as Shaun sort of said, we're now going to move up to the stratosphere, and I kind of want to talk to you about a couple of bits, how we can, or how climate impacts change quite drastically depending where we inject stratospheric aerosol, or SO2 in this case. So the sort of three main solar intervention strategies, stratospheric aerosol injection, and then the cirrus cloud thinning and the marine cloud brightening that we heard about this morning. And generally, we've kind of looked, especially in the SAI space, and stratospheric aerosol injection space, we look at kind of what the dynamics are doing and how that drives impacts. And that's definitely going to be sort of the main focus at the beginning of my talk. But I then want to touch briefly on like the impacts that we would experience under different SAI strategies. Oh, sorry, I don't know why that changed. Let's hope. Actually, I'm just going to quickly stop sharing because I have a feeling it's got timings on it for some reason. Let's change that. Cool. So just quickly share again. Yeah, so I'm just gonna, Will actually briefly mentioned about the GeoMote project, something that I'm relatively involved in as well. And in this phase, we're looking at cooling SSP 585, which is like a high emissions scenario, down to SSP 245, which is like a medium tier scenario. And we do that by injecting SO2 into the stratosphere. And then we're going to do that in this in these two scenarios or two strategies by injecting in two different locations. So the first one that I'm going to be talking about is G6 sulfur, and that is injecting between 10 degrees north and 10 degrees south. And then one of the newer sort of strategies that we're kind of talking about now in this space is using like a multi-latitude injection strategy, and we kind of want to see how that compares to the initial like early analysis where we always injected at the equator. And so in terms of like how much SO2 we're putting up into the stratosphere, that doesn't seem to change a huge amount between these two strategies. And so the blue line here is this equatorial injection. And the reason it's stepped is that it's done every 10 years of simulation. We recheck our temperature target and inject manually how much SO2 we want to inject to meet that target. Whereas with this new strategy, this setup, this G6 controller that we're calling it, the pink line is the total amount of SO2. And then these four coloured lines at the bottom of the different latitudes. And this is all very cleverly controlled by this feedback controller that was designed by a group at Cornell. And yeah, as you can see, the location doesn't change the total amount of SO2 too much. So both strategies are set up to meet a global mean temperature target. And as I mentioned earlier, in this case, it's the SSP 245 scenario. And essentially by the end of the century, it's offsetting 3 degrees of warming. And both of them do this pretty well. I mean, part of the sort of the setup of these strategies is that it has to meet that temperature target to within 0.2 degrees. And we can see that they do that really well. But then another difference to the G6 controller strategy, which is that multi-latitude strategy, is that this controller also has 2 other temperature targets that it wants to meet. So this first one is the interhemispheric ratio, so the balance of temperatures between hemispheres. And then the second one is that ratio between the pole and the equator, and that difference in temperature. And so interestingly, you can see with the interhemispheric ratio, both of our injection strategies meet this temperature target relatively well. And that's mostly to do with the fact that when we're injecting at the equator, it's seemingly symmetric. But interestingly, when we then try and meet this pulse equator ratio, the equatorial injection fails to do so. And by the end of the century, you have this positive bias at the pulse equator ratio. And actually, even when we're trying to control for this target, we kind of don't do the best by the end of the century, but otherwise it's relatively well controlled. And I'll come back to why a bit later. So immediately you can see when we look at the stratospheric aerosol optical depth, so like how much aerosol is in the stratosphere, the distribution is massively different between these 2 scenarios. So with the equatorial injection, we have this massively strong tropical confinement, and that's been shown to be particularly strong in UKSM, which I should have actually mentioned is the model that I'm using. And there have been comparisons to other models using G6 sulfur. And as Will mentioned, it's a really, GeoMet's a really good way of comparing these models and how they perform. And it's not necessarily as strong in other models, but in UKSM, we see this strong tropical confinement. And because we're not injecting at the equator in G6 controller, or I've actually called it G6 sulfur controller here, it's much more dispersed across the 2 hemispheres, and it's not quite so strong. And essentially, this leads to some real different effects in the surface temperature. So if we're looking at the near surface air temperature, in G6 sulfur, you can see why that pole to equator gradient has this positive bias, and it's because the pole has this really strong sort of residual warming, and the tropics experience this high cooling, and that's due to that large aerosol load over the equator. You don't see so much of that in G6 controller. It's a bit more ameliorated. You still have this high Arctic warming. And again, that's another feature of UKSM. I think someone mentioned that earlier about this Arctic amplification. So that's a problem we see in this model. But interestingly, when we look at this sort of, if we break this down into regions, I've highlighted here the regions that are outside of the range of variability in our target scenario. So you've got to take it with a pinch of salt. We only have 3 ensemble members for SSP 245, but essentially these regions are experiencing outside of the range of variability of this target. And obviously with G6 controller, you can see that's a bit less worrisome. But also with these high Arctic regions, we can see when we break this down regionally, and you don't need to worry about too much of the detail in this plot other than these are all the different regions of land, and the regions that I've highlighted in red are those that experience the most warming in this high emission scenario. And it's actually these regions here that we see a similar level of like high warming under SAI. So I'm going to swiftly move over to changes in precipitation. This is like a kind of generally known fact that under climate change, we're going to see an increase in precipitation. But actually, when we have a look at SAI scenarios, we see this suppression of precipitation and a decrease. And you can see that in the equatorial injection, there's a larger decrease and then a more sustained decrease under this equatorial injection strategy. And similarly to this, to temperature, it's not all equal. So regionally, we see these really stark differences. So just to break down this plot, so we're looking at the end of the century compared to present day. And you can see even in the 2 warming scenarios that there's a lot of things happening. We have increased precipitation, mostly in the Northern Hemisphere, massive drying over the Amazon, over Australia. Under the high emission scenarios, sort of South Africa. And we see almost similar patterns in SAI, but all sort of more extreme, especially over the Amazon. And the kind of breakdown of why we see these changes, I'm in the process of working on. But one of the things we can look at is the zonal precipitation change. And I'm not sure, the last time I gave this presentation on a projector, you couldn't see the grid lines, so hopefully you can. And I've forgotten to put a 0 line on, but essentially the 0 line is present day, and the light grey is the sort of, we say target, but we're not targeting precipitation, but the sort of target temperature scenario. And then on top of that is our high warming scenario, and then our equatorial and our multi-latitude injection. And you can see that under G6 sulfur, which is this equatorial injection, we have this massive drying around the tropics. And this is very much ameliorated in the multilatitudinal strategy. So one of the kind of initial thoughts is that perhaps this is to do with the sheer aerosol load that we have, causing much more cooling over that region. But also something that I'll come on to is potentially the impact of stratospheric heating. So here we're just looking at the vertical temperature profile by latitude. And in this first plot is just our warming scenario. Again, this is compared to baseline, our target temperature scenario. And you can see that when we inject to the equator, we have this really high warming in the stratosphere. And you can see that peak is pretty high. And we can really bring this down when we just disperse the aerosol more towards different latitudes. And this can have, there have been papers out recently discussing how stratospheric heating can impact the dynamics that we then see. So again, this is something that's kind of under investigation a little bit to see how that plays into things like precipitation changes. So yeah, this is one of the things I really wanted to sort of highlight. And how do we sort of begin to quantify the impacts on us on the ground? And one of the ways I've been trying to do that is firstly by breaking down by region. So these are actually the regions that we saw in that earlier plot, but also looking at some extreme indices. And that's kind of one way of doing things. And I think I'm definitely moving further into that space, and we're getting some interesting results. Sadly, I couldn't show you the most recent results, but yeah, one of the things that's really important about these indices is that they kind of mean more to people on the ground than necessarily like degrees of temperature change or like annual precipitation metrics, especially in terms of precipitation. So when you think about heavy rain days, we can all relate to when we have a massive storm and we experience that maybe more or less frequently, or in the summer, like if we have a longer number of consecutive dry days, or in the winter if we had a longer number of consecutive wet days. So that's a good way of sort of seeing how that might change on the ground. And that's kind of then when we can try and tease out some of the impacts that we see sort of more broadly. So when we look at this equatorial injection, so on the left hand side, this plot here is just the annual, so this 2 decades average annual precipitation change compared to present day. And if we just look at the Amazon here, we have this massive drying. When we look at something called the simple daily intensity, so basically how much does it rain on that day, we can actually see that if we just look at this bottom left plot, that a lot of that decrease is coming from daily intensity. And I'm not going to show you all the different metrics, but you can then look at the different metrics and see actually which of those is changing the most. And another one is the heavy rain days. So this is the number of heavy rain days is decreasing in that time period. So that's kind of potentially what's leading to that decrease. And then if we were to look at the multi-latitudinal one, we have this, again, decrease over the Amazon, but actually it's being controlled a little bit more by the consecutive wet days. So we're actually not seeing as many consecutive wet days. So yeah, I think that's probably where I'll leave things, but just to also say that we're going to try and compare some of these metrics with another UK ASM multi-latitude injectional strategy, because then we're going to, you know, as well mentioned, when you have two models and they're kind of doing different things, it's hard to say what's actually, you know, is it the model uncertainty? Is it the strategy uncertainty? Is it the scenario uncertainty? So one of the things that we're going to try and break down is actually see if we still see these similar pictures in a similar strategy, but under a different temperature target. And it'll be really interesting to have a look at how that would change. So yeah, I'll stop there.
Great. No, really great. We've got time for a couple of questions. Alice, I've got one quick question for you.
Yes.
Earlier on, you mentioned pole to equator ratio. Did you really mean ratio, or did you mean difference? Because you gave it as units of degree centigrade.
I actually meant gradients. So the actual metric escapes me now, but it's kind of the gradient, like I guess it is the difference between the pole to equator in terms of degrees. Yeah.
There's a difference. Perfect. Okay, super. We'll take some questions. We'll take Hans first and then Alan.
Thank you very much, Alice. That was very, very interesting. I think, although the word has not occurred yet this morning, I mean, these are all means. I mean, the larger objective, of course, that we have is to try to contain sea level rise, because we've got billions of people and trillions of assets along the coastlines. You said two things that took my interest. One, you said reduce precipitation. If I would have to translate it in political environments, that will be a showstopper because of the food production challenge and also what you said about the Amazon. And the other one you said is residual heat stagnation in the Arctics. Well, would that then not mean that we are all doing this for nothing? Because if you get the cooling around the equator, even at a plus minus 30, but you get heat stagnation in the Arctic, we'll still see Arctic melting and hence sea level rise. Could you elucidate a little bit more on that?
Yes. So in terms of the first point was about sea level rise. And I guess we sort of saying averages of temperatures. So that's not something I've particularly looked into. I think it's definitely something that's become more of interest, like in recent papers that have been coming out. So I can't necessarily speak on that front. But in terms of the that residual heat in the Arctic, again, it's very model dependent. So in the equatorial injection strategy, we see a much higher increase of or residual increase in temperature versus the poles, versus the equator. But when we change our injection strategy, we don't see that as much. And in other models, we don't see that warming in the Arctic as much at all. So that's one thing that we really need to bear in mind when we actually, and something I probably should have mentioned is that when we're conveying our results, it's hugely dependent on the model that we're using. And really, it's the model into comparisons that show that uncertainty range. In terms of saying that it's that there's no point to it, I guess, is that do we want the warming? I mean, obviously there are going to be feedbacks to having that Arctic amplification, absolutely, but it's the sort of the general picture versus the specific regions. But that's a huge problem about SAI in general, is that regionally it's hugely different in comparison to the global means.
Great. Alan.
Thank you, Alan Gadian, ex NCAS. Very interesting talk. You highlighted 2 points, and I'm going to try and come in your sport on the second one. The pole to temperature gradient is absolutely critical in the ice, for the ice in the Arctic and the Antarctic.
Alan, do you mean pole to equator difference?
The difference, yes,
Right,
temperature
okay.
gradient, right. So which you highlighted, and that is partly due to the effect of the aerosol, and you've very clearly shown that there is effective warming at the poles. So yes, I mean, it's a very interesting result. But the second point, so I would like to ask about the other models. The second point is on the rainfall. Now, there are some results out for MCB on the effect of the rainfall changes. Now, you showed a slope of about 1 Clausius Clapeyron for the increase in rainfall. So every degree sea rise, there's a 7% increase in precipitation. But when you say there's a precipitation decrease in certain regions, you are doing it compared with now and not compared with the increase in precipitation. I would say 7 degrees C is wrong. It should be the 7% increase in precipitation. I think it should be 10 or 20%, and certainly so you're comparing the precipitation decrease with now and not what it will be. So actually plot those, and then I think you might find it's different.
Yeah. So do you
want to respond?
I was just going to ask the precipitation. Do you mean the map plots or the gradient? Because yes, the gradient plots are.
Alice, I think it was a general.
It was a general point, but the point is that you're comparing it with present values. Going to increase. You've got exactly the same regions as MCB for reduction with double CO2 and MCB. So you should be very careful that you're not comparing with present, but what is going to be in the future. But the major problem I have is with the warming poles. That really does. Don't shoot yourself with that.
Okay.
Yes, one of the discussions we've had is very much about how to frame the results. So it's definitely an important point. Thank you.
Now, let's try an experiment and see if we can get Brian von Herzen to ask his question by unmuting himself. It should work.
Yes. Can you hear me now, Hugh? Very good. Thank you, Alice. Very interesting presentation. I have a question in 3 parts. And that is, first of all, please confirm that there's a net stratospheric flow towards the North Pole in the Arctic. And then the second part is, could that poleward flow limit the duration and time scale of stratospheric particles that are present in the Arctic? And the third is that I note with interest that if we injected stratospheric particles in the Arctic itself, the threshold of the stratosphere is actually lower. Is there any reason that Arctic injection may not have been considered so far?
Thank you. So the first point, yes, I do believe there is stratospheric flow towards the Arctic. I think just in terms of where we inject in UKSM versus other models, we don't see as much transport. Your second question was
about the duration and time scale. In other words, if there was Arctic injection, maybe the duration and time scale of those particles would be more finite if there's a net poleward flow.
Yeah, so it's one thing that it's actually it's on my list of things to have a look at is the sort of the deposition rate almost, to see how quickly we're having aerosol being sort of transported and removed. So I don't know the answer to that question now. On your third point about Arctic injection, a colleague of mine's actually been running some simulations with 60 degrees north, so we should have more information on that. I know a group at Cornell's been doing that with CESM. And I have a feeling they're not injecting at as high altitude because you don't need to in the Arctic. But I haven't seen any of the results of that yet. But it's definitely it's coming on its way in terms of that research.
Oh, that's great. I'd wondering if you'd be willing to speculate if that might actually reverse the temperature difference that we see from pole to equator, because
so I think
the Arctic.
Yeah, so I think one of the initial experiments was doing 60 degrees north and 15, as in and north and south. and the Arctic, so the polar temperatures were brought down in UKSM, not by loads, or not by as much as we would expect. We're now considering 30 and 60 to see how that would change, and also doing like a seasonal 60. And the group at Cornell have done a seasonal 60 where you are only injecting, I think, in the springtime. So you're actually having less aerosol load to maximize on that seasonality side of things, so that you don't need it up there in the wintertime. And I don't know the results of those off the top of my head, but I think it definitely, I mean, in CESM, they don't have as much of an Arctic amplification, so it's difficult to then say what that would look like in UKSM, but I would imagine, I'm hoping at least in the seasonal 60 degrees north, we would see much more of a difference.
Wonderful.
But yeah.
Great. Well, thank
you.
So implied in that, if they're doing it in the spring, implied in that is actually a shorter time scale, and hence Brian's second question, that it's suggesting that indeed there is a shorter time scale. Thank you ever so much indeed, Alice. Please stay online, all right, because we'll try and bring you all together towards the end of this session. And Brian, thanks ever so much indeed for your questions. We're now going to be joined by Andrew Lockley, who has a position down in London, University College London, but is also an independent researcher.
I don't.
But we're going to be hearing from Andrew, who is always incredibly creative in his thinking and provocative in his thinking.
Yeah, you can say that. So I'm going to get my 10,000 steps in by wandering around the stage while I'm talking. So today I'm going to be talking to you about SATAN, which is the Stratospheric Aerosol Transport and Nucleation Experiment. And this is a project that I did in conjunction with European Astrotech. And my glamorous assistant Hugh is going to do my slide transitions for me so I can continue jumping around. So if you're the kind of person like me who can only concentrate on one slide in a presentation, this is the slide to concentrate on. Here's the key points. So it's the first stratospheric flight of a geoengineering aircraft. It's the first confirmed stratospheric aerosol injection. We did it by sulfur dioxide precursor, so we didn't monitor the actual aerosol formation. Key point, it's an engineering test. It's not an environmental test. We're not trying to measure what happened in the environment. And it certainly isn't a deployment program like Meg Sunsets. We're not trying to deploy geoengineering at a meaningful scale. We're not looking to use this technology to scale geoengineering. And probably the most important point, it's upset a lot of people. So what's in a name? This tweet's quite good, I think. Antonio said it's the scientist in the story at least has a sense of humor. So that's not our balloon. I wish we could afford artwork like that, but we couldn't. It was done on a shoestring. And it's obviously it's a controversial field. It's a tiny experiment with no detectable environmental impact. And what we wanted to try and do with this naming is just to try and challenge the apocalyptic rhetoric around experiments outdoors. There's a lot of evidence building up to show that people vastly overestimate the downside of scientific research. And we want to try and embolden researchers to be a little bit more less worried about their work. So the background to this, there's a kind of Faustian bargain with stratospheric aerosols, and as our CO2 levels rising, the anthropogenic aerosol is falling as we clean up our emissions. And even if we keep CO2 levels stable, we're still going to see significant warming from the loss of aerosols. So, you know, do we have to make a choice as a society to replace the unwanted aerosol load in the troposphere with stratospheric aerosols to keep us cool? And James Hansen, if you think that I'm the first person to use religious imagery, James Hansen has been tweeting that. So if you want to shout at me, you can shout at him as well. Next slide here. So what's our objectives? What do we want to do? Well, we want to create something that looks a little bit like the top image and not as much like the bottom image. So we want to have something that's so cheap that you can use a lot of them to create and monitor an aerosol cloud without creating a whole bunch of trash rain. So we want a reusable aircraft capable of micro deployment, carrying some simple instruments, able to effect some position control, more of that later, and cheap enough to swarm. Kind of like Scopex, but about several orders of magnitude cheaper. Next. So here's a schematic of what we're trying to do. So you've got a big lofting balloon, a big H2 lofting balloon, or helium in our first experiment, and a little ballast balloon. We use carbon dioxide in our first experiment and sulfur dioxide in the second experiment. Separate valves, the little bow ties are valves. pumps in the later experiment, and we have a sensor and avionics suite in the middle. And the idea being that this is kind of neutrally buoyant. So if you let a bit of ballast gas out, it goes up. If you let a bit of hydrogen out, it goes down, right? And that the idea is that that's the central kind of concept behind the craft. Hugh? And the real design is obviously massively more complicated. I don't want to go into that in detail, but I just want to show you all of the different things that we had to worry about. So you can snap that if you want. So the payload and instrumentation. So we've got a climate active gas payload. You know, we want to be able to take some sulfur up to the stratosphere. We had an environmental sensor suite, so we're taking the standard things you put on a balloon, pressure, humidity, and temperature, but we also included the toy particle counter. And it's a toy particle counter not because it doesn't work, it does work, but it just doesn't monitor aerosols in the size range that we need to monitor to validate the experiment. And the reason for that is the difference between a toy one and a real one is about £25,000. So we decided that was probably superfluous. We've got position sensors and actuators, so we know sort of how high it is, whether it's going up, whether it's going down, and a camera to take pretty pictures. So the lab tests, they were easy peasy. We rotted some balloons in latex. Thanks, Hugh, for your assistance for that. I did that in your lab. Filled and emptied the balloons, tested the electronics and the valves. It all worked well indoors. And then we went out to the real world, and it didn't work. So we had a ground test. We filled it up, flapped around in the wind, and it broke because of the wind. Loads put too much torsion on the neck. Then we had flight one, so we had a dummy payload with CO2, flew up to the stratosphere. The main computer shorted out and didn't work at all. The backup computer froze because it got too cold and it didn't work. But it did reach the stratosphere. So you can see the temperature rising at the bottom. So we went through the tropopause. That was our flight officially. Yay, we got into the stratosphere. First year engineering aircraft. Second flight, we had an active payload. It got to the stratosphere. This time the vents didn't work. Everything else did. The payload balloon passively burst. You can see it shrinking as it went through the tropopause. It was all the gas condensed out. The main balloon burst, terminated because the vents didn't work. The balloons eventually burst, but they burst in the right order. You want the toxic one to burst first and the non-toxic one to burst later. Particle counter didn't talk to the main board, and then we had carried out a successful airstrike on Royston, which is sadly still there, but we will work on that on our next flight. The vent problem is pretty fundamental to this. So basically, as the balloon rises, it expands and you eject some gas out the bottom, but you don't eject enough gas out the bottom to be able to overcome the expansion. So the balloon just rises to infinity and beyond. You can't control it. That's a big problem, but we can get around it. Next slide. So these are our results. The green's not showing up, but basically these should be green. We basically achieved everything, most of what we set out to do, apart from the orange ones we only did on the ground. Most of the rest we managed to achieve. We didn't get reusability, but you know, can't have everything. Next thing, so the learnings, it basically works-ish. It's slow to vent and that limits your controllability. So you've got two choices. You either very, very, very slowly rise, which you can't do in UK airspace because you hit airliners, which gets really expensive because they're like millions. And then, or alternatively, you're a sacrificial lofting balloon that drags up your neutral buoyancy craft, pops, and then leaves the neutral buoyancy class floating along in the breeze. You can't have both UK use and no litter. That's fundamental. It can't be overcome. So it seems impractical at scale. And also you've got the issue of leaking lifting gas. This is not a organized solution. But we didn't expect what happened next because no one expects the Spanish Inquisition. So we had an unpredictable leak and not in a balloon. We submitted it to the GMIP conference, and then suspiciously, just after submitting it to GMIP, we got told we were not allowed to go to GMIP, but we got journalists starting to call us. And so MIT Review did a piece on us, which was sort of all right. And we got told lots of nice things by colleagues. Basically amounts to engineering experiments on real experiments. We're unserious. It's a stunt. We're cowboy. Although that was David Keith. He said we were less cowboy than Make Sunsets, but still cowboy, but less cowboy. And I got told by someone, I can't remember her name or even pronounce it, that we were ethically dubious. So, you know, this is Satan. You kind of expected he would be. And now I'm academically homeless, which is a fairly predictable result. Just to sum up with a quote from Satan by Orbital, it's better to regret something you have done than to regret something you haven't done. So there we go. What's the future bring? We've got several ideas. So we might use a Rosier balloon, which is a helium balloon with a hot air balloon section in it. That might overcome some of the fundamental limitations. If we can ignore the loss of gas, we might have something that's a bit like a sky dancer folded over at 0 pressure that you then release, and it lets all the gas out, so you don't have a problem with a tiny little vent that you're trying to use. Or you might just sack it off and do this. So we've got another experiment series called Chemtrails. I won't be bothering with the acronym for that. That is based on having a very high lift drone, similar in structure to the Global Hawk, that will test a completely different way of delivering. So inevitable plug, this is nothing to do with the experiment at all. This is just telling you about the information services I operate. They're impartial. They're nothing, about telling you that our experiment is great or promoting it in any way. So I do the Reviewer 2 does geoengineering podcasts. I've interviewed several people from the community on that, about 100 episodes we've got now. I run the geoengineering on Twitter. If you don't do anything else, follow that, because you just get a fire hose of every paper, every news article, all on there. I run the geoengineering Google group, also contribute to the CDR Google group, and I do a Substack, which is carbon removal updates, in conjunction with my glamorous assistant, Aisha. I've got 2, one's Hugh, one's Aisha. And that's my email address if you want to send me verbal abuse. So thank you very much for listening. I'm happy to answer your questions.
So I said he was provocative. That was an understatement.
I'll do my own mic running.
So any questions from the room?
Comment.
Keep the comments short, because we've got a question from Hans Allen.
Just to say, using balloons, I've spent a lifetime doing it, is very difficult and not easy, and totally understood.
Andrew, do reply.
Yeah, I do want to reply. Yeah. I think that engineers are treated as the kind of idiot cousins of the academic community, and I find that people often rely on engineering and say it's trivial, but the people who say that engineering is trivial has almost never taken the trivial step that they say is trivial. Like, engineering is always trivial when you've done it. You just plug it in or ride it or drive it, and it's trivial. I had a trivial journey today in my car, and it was trivially easy to do it, but it's taken a century of engineering to get there.
Hans, do wait for the microphone. Thank you.
Thank you. First of all, you got the kind regards of Leon Simmons, who I spoke with yesterday, and you didn't disappoint. He said this will be a fun presentation. It was indeed. Many years ago, when I did my MBA, we were given a book called International Marketing Blunders. And there was a company called General Motors in Detroit, and they wanted to launch a small car from the US in Spain, where it would be a medium-sized car, and it's called the Chevrolet Nova. And after millions of pounds or euros in advertising, they didn't sell a single car. And then they found out that Nova actually means doesn't run. So if you market a car that actually is named doesn't run, it won't run. So you did get the red for the bull price. What's the thing that you want to convey? Is this, it was this associated with the SAMI experiment, what you just described? Because I looked at the map, it was Aylesbury, so that was here in the UK. There was also an experiment like 2 years back in SAMI, Northern Scandinavia. Was that something they want to release 50 kilos of sand?
So, yeah, what you're talking about there is the Scopex experiment, which has come out of David Keith's group in Harvard, who they've spent 10 years talking about launching balloons and have not launched any because they are not willing to take the step that I have taken. Fortunately, I'm just in a position where I don't earn money from academia. Like, no one can fire me and ruin my life, right? So I thought, well, I'll be the buffalo that gets pushed into the water in front of the crocodiles by all the other buffalo. I'll get savaged, and then you lot can cross the river behind me. I've not lost anything material. And the problem with Scopex, not only did they spend 25 million quid and not launch a single thing, but they basically had a strategy that they weren't going to do anything until everyone in the world was perfectly happy with everything they were doing. And inevitably, no one was. And so, you're never going to get to the point where you please all of the people all of the time. And so they've done nothing. Now, I'm not berating. There's some decent papers that have come out. They've trained a load of PhDs, people I really respect, like Colleen Golier have come out of that group. But they didn't do what they set out to do. And I've, for about 10 grand or whatever it is that we spent on this, we managed to do, well, we've done the mission. what it's come down to is a lot of people who've never done any geoengineering shouting at someone who has done some geoengineering and telling them they're not a proper geoengineer. It's a bit, okay, whatever. Hello,
Okay,
Alice.
Alice.
I've got the mic
Yes.
now, Alice, so I can actually say that I love your little grid of all of the different things that could go wrong with the weather. I think you should call it the British Weather Moaning Index and publish it as a separate piece of work.
In the medical sphere, they use a different acronym for BMI.
Okay. Anyway, you can ask your question now.
Yeah, so I guess my question is, so with regards to the name and the experiment, did you not foresee that there would be pushback with the name? It's like my first question. And then my second question is it not wise going forward with SAI research and the work that everyone's doing, knowing that it's a controversial subject, to engage in some community outreach, I guess, before you do an experiment and then call it Satan? I feel like if we're moving forward into a space where this is becoming more of like an actual piece of, you know, research that could potentially be implemented, whether that's a good or a bad thing, should we not be trying to do it to the most socially engaged best practice methods and not calling it Satan?
Well, I told you,
even though I appreciate
I told you how,
yeah.
I told you how well it worked for Scopex. Hugh, how well did it work for you when you tried to do some public consultation?
Well, I have to say, the public consultation process is very long-winded and, as far as I can tell, always unsuccessful. But having said that, you look at what's been going on in Great Barrier Reef with their marine cloud brightening stuff, but maybe you know, the comment that Edmund made earlier was that if it's seen as, you know, clouds are white and fluffy and nice and everyone loves coral reefs, but sulfuric acid being launched by, you know, somebody who looks like you, Andrew, is so yeah. I mean Alice has got a fair point. So I don't know, but in 10 years' time we'll look back and figure out how we got there.
There's a great sketch that I refer to. I wish I got time to play it. Where in Casino, where was it Casino or The Devil's Advocate, where Al Pacino is very drunk in a restaurant and he runs around shouting, people like you need people like me. I'm the bad guy. You need to be able to point to people like me and say he's the bad guy and make yourselves feel better. And the only finger pointing, I haven't had any public backlash, particularly no nasty tweets or emails, nobody coming around my house and trying to shoot me in the head or anything yet. But what I have had, there's a lot of denouncement from colleagues, and that, you know, perhaps I'm the bad guy you all need.
So we're going to move on, but
Andrew.
Yeah, very good. And what I would say is I hope this afternoon that we'll talk a little bit more about framing narrative and some of the issues on governance. And there are some really interesting pieces of recent research which we'll share this afternoon, but sort of looking at actually how negative is this whole subject and who's actually expressing those views. More of that this afternoon. We're now going to be joined by John. Just in terms of FYI, we've got Clive online who will, we'd suggested about 12:30, but so Clive, if you're listening, I'm going to guess more like 12:40 for your ETA on screen, as it were, for your presentation. So John, over to you.
If you stand there, John, I'll operate the slides for you. The microphones are there. That's fine. Yeah, that's fine. Yeah, if you go there.
Okay. I can't quite match.
Yeah, that's it.
I can't quite match Andrew for the speed of delivery and doing it all completely without notes and making jokes. But I'll have a start. The last time I've been at Cambridge, it was before CCR was set up. I was meeting Sir David King about climate change and the need to refreeze the Arctic. Stephen Salter, of MCB fame, was with me persuading Sir David that marine cloud brightening could do the job of refreezing the Arctic. Sir David's response was, "Thank God I don't have to persuade people
that we need to inject SO2 into the stratosphere. But ironically, that's exactly why I'm here. And David has scarpered. I've only got a few minutes, so I'm going to quickly defend stratospheric aerosol. I don't really need to do very much because Brian von Herzen has pointed out that if you inject stratospheric aerosol at high latitude of 50 degrees, 60 degrees, perhaps even lower, 45 degrees, it only has a short lifetime compared to the equatorial injection. So you can limit its lifetime to a few months. You inject in late spring or summer, and it's all gone by the winter, and that's due to the Brewer-Dobson circulation in the stratosphere. Directs everything slowly towards the pole. If you inject it from the equator, it takes perhaps a year and a half to reach the pole, and it will therefore be affecting the ozone hole, and it will cause warming, as Alice was pointing out. You get warming at the pole. That's the last thing we want, because what I want to do is to refreeze the Arctic. That's our common denominator, I think, here. That has to be the #1 goal. And the objective, of course, is a brighter future for our children. So we're not going to get there from the IPCC. They're in a bubble of denial, obfuscation, and cognitive dissonance, whereas we believe in the truth, honesty, and integrity. So we're heretics. We're running against the common thread, and we should be proud of it, and we should be fighting hard. And we're also engineers, which as Andrew mentioned, is a downgraded profession. We must be proud. We're building a bridge to a brighter future. And so what I'm going to do the rest of my talk is to talk about some of the kind of ammunition in this fight, or the kind of things that might be useful in persuading people that we're right, and we've got to do this, and we've got to do it jolly rapidly. I probably can't. I can use that little button there. So here's the, if you can look at the diagram.
Well, unless you want to use the mouse here, you can on there.
Oh, I can use a mouse, can I?
Mhm.
All right.
Yeah, but you can look at it on here, you see.
Oh, right, okay. So we've got a denial of this diagram. Everything I say to you is completely taboo in IPCC. You can't get anything like this published because it's real. It's the reality of what's happening. And one of the few people who's pointing this out is Jim Hansen. So we followed Jim Hansen's gradient here. So he says the global warming is going to rise double in the next 25 years compared with the previous 40 years. So that we've shown that. And you get these brown curves going up here, and you're about 4 degrees by 2075. That's in the 50 years' time, we'll be at 4 degrees. And that, of course, doesn't allow for tipping points, whatever they might produce. And it's more or less whatever you do with your emissions. The lower curve is business as usual. If you do very rapid decarbonisation, you get more effect from SO2. So another thing, so this is completely against what the IPCC has been saying. Everything will be fine. They say that the risk of tipping points is going to be avoided at 1.5, but actually the tipping points, which we should really call tipping processes, were activated in the Arctic in 1980 back here. Excuse me. And that's and so what we want to do is to build a bridge to bring the temperature down, the Holocene norms for our future well-being of humanity and ecosystems as well. Yeah, okay, next slide. Right, one of the things that is not generally recognized by and talked about by the IPCC is how the Earth system works. If you're going to change a system, you need to understand the system, and the system is extremely clever. The Earth system has a mechanism which takes this Milankovitch signal here, peak. That's warming in the northern hemisphere summer. And 12,000 years ago, it was at a peak. The Younger Dryas period ended. There was a warming of 50 degrees, sorry, 10 degrees in 50 years in the Arctic. And we're seeing very similar thing happening today. So that's what learning from experience. And this extraordinary system is amplified in the Arctic through albedo loss. So the warming signal heats all the water, surface water, north of about 50 degrees. It's all flowing towards the Arctic. The Arctic is warmed. The sea ice retreats and snow as well. And you start getting positive feedback, and that's amplified and so the Arctic warms of sea ice becomes seasonal, very little in the summer.
Next
right, okay, so that mechanism of amplification is terribly important. And the consequences of rapid warming in the Arctic are three things. There's the melting of the Greenland ice sheet, which has implications for sea level rise. There's methane, which has, if it increases by to a megaton level, would aggravate global warming. But the main one, which is generally not understood by or recognized or publicized by the Met Office people, is that the gradient between the between the Arctic and the tropics is produced. That causes the polar vortex to wobble. The jet stream meanders. There's less energy driving the jet stream wave. This wave here, it's called the Rossby wave. There's less energy in that, and that results in weather extremes. And weather extremes is what people are observing now. They're talking about the climate crisis. It's not explained by IPCC what the source of this climate crisis is. We do know where we have the truth, we have the integrity, we've got to get it across somehow. I don't know how we're going to do it, but we've got to do that. That's our mission. That's the purpose of what we're all doing. So I want to leave you with that message.
We've got to move on.
Just one more thing, but it's very tough to cool the Arctic. The albedo loss up there could be as much as 1 watt per square meter, and that's to be compared with 2 watts per square meter from CO2. So an MCB is just not going to be enough, I'm afraid.
Okay, John, what we're going to, in fact, what we're going to do, because Clive is running to a tight schedule, we're going to go straight to Clive, assuming he's online, and then we're going to have questions, if that's okay. Yeah. All right, many thanks indeed. We're going to be now joined by Clive Elsworth. Thanks ever so much indeed in your busy schedule of teaching today, Clive, to be sharing with us. So we've got your screens, your slides on the screen. The floor, the virtual floor, at least in your case, is yours.
Thank you very much, Shaun. Thank you. That's great. Okay, so this is about a number of things, including black carbon aerosol and potential proposed solutions. They're not quantified, but things to be aware of, things to look at, things that would be nice if people considered them. I'm actually going to
Clive, it's not critical, but if you go to slideshow, it might be just a, yeah, that's it.
Better? Yeah. What I'd like to do actually is go, I'm just going to come back out of that just for a second. And because this is very short, I've only got about 10 minutes, is go to my last slide, the conclusions, and say that there's rather lower hanging fruit than, this idea of sucking 1 trillion tons of CO2 out of the atmosphere or even going to net zero. I very much agree with John and no doubt other people that have spoken today that cooling interventions are needed. And so this is what hasn't been quantified, but I'm going to go back to the rest of my slides and suggest some things which most people I think are not aware of, and certainly not in the press. To refreeze the Arctic, most urgently Greenland. We've just seen a picture of Greenland. There's a short summer period where it's often open skies, just blue skies, sun shining on the ice, where either haze or brighter clouds, when there are clouds, should be able to cool the ice, prevent it from melting so fast. For the rest of the year, clouds provide a warming influence on the ice, and if the cirrus clouds can be thinned, then perhaps this low-lying warming cloud over the ice may be able to be thinned. I put this or something like it to Jim Hayward some months ago. So he's Met Office guy and professor of maths at Exeter, who said, don't just do the Arctic, what about the big oceans? So we know that, just as John said, warm water flows into the Arctic, makes the air more humid, presumably thickens the clouds there. So this is part of Arctic amplification. And so John, I've just heard John say marine cloud brightening isn't enough, but I know that Stevens says that maybe it is to cool the oceans. It certainly can help. Another thing is diffuse ocean fertilization, with iron salt aerosol. So let's go back to the beginning. And so black carbon aerosol, here's some Arctic haze, and this is the shocking sight recently from Peter Wadham's, one of his many pictures of the ice, part of the ice in Greenland with black carbon aerosol, you know, having deposited on the ice. It's no wonder that it's melting so fast. So the IPC, one thing they have said is that this is one of the easiest pollutants to address. Okay, and 55% the warming influence of CO2. Why are we concentrating so much on reducing CO2 emissions? I mean, yes, it does need to happen, but when 55% of that warming influence of CO2 is coming from black carbon aerosol, it has a global warming potential, which I only realized this myself recently. I mean, we worry about methane being 80 times as much as CO2, but what about nearly 4,500 times as much as CO2 over 20 years? Of course, it doesn't last as long in the atmosphere. It goes away, but anyway, so this is what they've said over 20 years. And John has just said, so this black carbon aerosol alone, a radiative forcing of a watt per meter squared. And I've seen even higher than that, actually, but I've pared it back so it's not just the maximum one, including the snow ice albedo effect. Okay, and where does black carbon aerosol come from to get into the Arctic? The answer is all over the place. So even for as far as where's Southeast Asia, and how come? It because it warms up in the sun, it provides what I'm calling a microconvective uplift. There are other fancier names, but we're currently debating with Franz what to call it. But anyway, it heats up in the sun, and it therefore drifts up by heating up the air around it, and goes into the stratosphere. And certainly it's not just us saying this. Is Susan Solomon released a paper in recent years saying the same thing. And it's also depleting ozone, because it takes ozone up there, takes ozone destroyers up there, which we've got a slide in just a moment. This is Brewer-Dobson air circulation, which no doubt has been mentioned already. Okay, it catalyzes its ozone destruction on its own. If we can't get any funding for solving the climate, maybe there's certainly money for saving the ozone layer. Perhaps people can help us with that. So black carbon converts and absorbs halogens. We're working on a paper at the moment. We've identified that many reactions. Here's an example, a very simple example of a reaction. HCl plus oxygen producing chlorine molecules. And black carbon it contains many graphene planes, so very thin sheets of carbon that efficiently absorb hydrophobic substances such as methyl halides. Methyl halides, like chloromethane, are produced naturally from vegetation, so you can't get rid of them. Vinyl chloride comes from landfills. And so at the edge of graphene planes, you have these, what chemists know as redox moieties. They catalyze redox reactions, which is most of chemistry. And here's an example of a redox reaction with halogens being produced. And so we've got methyl halides, and I think that's vinyl chloride there, and just lots of halogens. So iodine and bromine are very strong ozone destroyers, unfortunately. So that's a slide on ozone destruction. How to reduce black carbon emissions? Well, there's a very good Wikipedia article on black carbon. So I'm not going to just repeat what that says. It lists a whole lot of things. I mean, we've reduced the black carbon coming from power stations in the rich industrialized world. It's filtered out. It filters out the fly ash as well. It's solved the acid rain problem. They can't afford to, well, they don't spend the money on that in other parts of the world, Southeast Asia. But if we want to spend a lot of money solving the climate crisis, perhaps those people might appreciate a little bit of help. Okay, so this slide really focuses on wildfire prevention. There's a great deal of black carbon, of course, comes from wildfires. We know that forestry management can help with that. I don't think so. I'm introducing the idea of terrestrial cloud brightening. marine cloud brightening is a very good idea. We're fully supportive of that. How about, would it be possible to make an aerosol over land? If so, if it could be used to provide haze and again brighten clouds over land, over areas, at-risk areas, months before the fire season comes along, perhaps they might be kept moist, and so the wildfires would not be so bad, or maybe not even happen. Maybe not happen. Okay, so this we're calling, some people have heard of this before, but we're calling it artificial Loess dust. So Loess dust blew around an awful lot in the glacial periods. It comes from glaciers. They grind the bedrock, and there are huge deposits of it all over the world. And it's very, very fine dust. It's makes land very fertile, actually, where it lands. We're saying that we can produce it from vapor, what we're calling vaporous chlorides. Okay. I've got a slide showing that happening in a moment, even a video. And so,
Clive,
yep,
Clive, just 4 minutes so that we can get some questions for you.
Yeah, sure. Go real fast. Okay, so this, and it degenerates to clay on sedimentation, and it also photocatalyzes methane depletion. Good. Okay, and here's a picture, so I won't show you the video. Here's a picture of a plane in the 1920s squirting out titanium tetrachloride. And this, so we're not talking about squirting out liquids with, okay. But we know that people will say, well, what about if you stop doing it, there'll be a termination shock. We're already in a termination shock because there's less pollution and so there's less cooling. What can be done? Artificial Loess dust, but also, as I mentioned, diffuse ocean fertilization. Here's a picture of wherever there's chlorophyll, and you see a pretty close correlation with clouds. Phytoplankton make dimethyl sulfide, which oxidizes to sulfuric acid aerosol. People then mention which nucleates marine clouds, most marine clouds. People say, well, what about the moral hazard argument? If you look at mining capacity, there's under strain. People are now talking about digging up the oceans. Okay, and I think John's just mentioned 10 degrees C warming from Jim Hansen. Cooling interventions are needed. And there's my conclusion again. Okay, I'll take questions, and thank you, Franz, for joining as well. I work closely with Franz on this stuff.
Thanks ever so much indeed, Clive.
Okay.
So we're going to take questions, and actually, obviously, we've got John as well. So really, first of all, any questions from the room, and I will be asking those of you who are online, please do feel free to post your questions in the chat, or if you want to feel like disturbing us in the room, then put your, as a way of engaging as well, please put your hand up online, and then we'll get to you directly. So first question, Andrew, nearer you, Hugh, Andrew Lockley in the back.
Hi, maybe I missed the detail, but the absorption, are you suggesting that it strips the halogen containing compounds from the stratosphere and thus protects ozone, or are you suggesting that the net effect is that it renders them more reactive by binding them temporarily to the surface? I wasn't quite clear on that. Yes, I also wondered if you can go into a little bit detail about the Loess dust.
Yeah. So black carbon aerosol collects halogens from the troposphere as it drifts up to the stratosphere. So these halogens have a vapor pressure, and the pressure is much lower in the stratosphere. And black carbon also gets aged and destroyed partially itself in the stratosphere, and these halogens get released into the stratosphere. So it's delivering ozone destroyers into the stratosphere. That's the point of that. In quantity, because like activated carbon, it's a very strong adsorber of these substances, and so it takes them up into the stratosphere. And again, this is what Susan's on. Yep.
Another question from Alan Guardian.
It's put to both John and you, Clive. The curve John showed a warming of the planet, which is in disagreement with Charney's original warming of the planet, which is much more rapid. So Jim Hanson's 10 degrees Celsius is, I think, very relevant. If you look at IPCC, they say clouds warm the planet. That's what it says on page 927, clouds. So I totally agree with you. But where I disagree with you is that the fact that MCB can't do very much. But the point is, if you look at the guidance for the Office of Nuclear Regulation, which controls the building of nuclear power stations in the UK, if you look at the latest CCRA3 document, you will find that the figures are much more online with what you're saying. Well, not what you're saying, John, because I think you underestimate the warming. But the question is, everyone talks about IPCC. There's need. Do you think there's a need to somehow publicize? The Office of Nuclear Regulation controls how you build a nuclear reactor in the UK, and there is no dissemination of this. So do you think both of you, we should use these documents to put pressure on governments?
So I'm going to ask, actually, John, would you respond first before I jump to Clive?
Where you at?
Yes, I think we should present these documents. I'd love to have them published somewhere. At the moment, there's no every single publisher seems to be in the hands of the IPCC and the government control and so on. So it's very difficult to get across. I have produced a report to an organization which might take a more of a security aspect of this, because it's a huge security issue, what we're talking about. We've got George Soros on our side, thanks to Sir David King, talking about refreezing the Arctic. We must build on that. I hope CRC will be, sorry, your organization. I'm trying the Bulletin of the Atomic Scientists. I've written them a letter. I haven't sent it yet. I'm trying to get signatures. So I'd like everybody here, please, to add their signature to my document, which will have that diagram as an attachment.
Okay. Clive, would you like to reply to Alan's comment as well, or not?
I'm not familiar with these documents, but if they're saying that they see, strong warming in the pipeline, then yeah, they should all be published. That's about all I can say, really.
Right. Any other questions? Any questions online?
So Isabelle can unmute herself, I think. And
thank you, Isabelle.
Yeah, so I have a question to Clive about the terrestrial cloud brightening. I didn't quite understand the reasoning. So you're saying you're hypothesizing about putting dust into the atmosphere.
Yeah.
Dust in the atmosphere is not necessarily a cloud, right? So can you just explain a bit more?
Yeah, well, the atmosphere contains aerosol dust, cloud condensation nuclei. This is what clouds droplets nucleate over. There's a lot more of it over land typically than over the ocean, because there's a lot more sources of dust over land, but also pollen. There are also substances come from vegetation. Isoprene is a very large amount of isoprene that's released from vegetation, and it oxidizes in the air to form solid little particles. And these are typically very acidic, both over the ocean and over land. But they're hygroscopic. They attract water vapor and they nucleate clouds in supersaturated air. So this is known. There's a lot that isn't well understood or can be modeled easily with clouds, because they're very complex. They're complex interactions internally.
I would disagree with that, because cloud microphysics are a major uncertainty. And there's various pathways also of cloud formation, which are really hard to model. So in effect, I would say that it's really hard to predict such an effect from seeding over land.
Okay.
Okay.
Maybe
So
you know more than I
just
do.
mindful of time. Well, Isabelle, thank you. You're right. It is incredibly complicated. And in fact, Isabelle, we're grateful for the Centre for Climate Repair working with TU Delft. We should have made it very clear at the very beginning. There's a partnership between the Centre for Climate Repair and TU Delft as part of this whole endeavour to try and further our knowledge with marine cloud brightening. And in broad brush terms, the TU Delft team, the cloud physics details of that and the expertise in that being brought to bear on this problem, and in large part the efforts of the Centre for Climate Repair on the experimentation side of droplet generation. Peter Wadhams, the floor is yours. A very brief question because we're running out of time, but we were very eager to hear from you.
Okay, thank you very much. And I wanted to thank Clive for showing the picture of black ice on Greenland, and to say that there's actually quite a large project going on at the moment where we're trying to map the extent of the black ice and doing a Raman spectral analysis to look at what the components are, because they include things that you don't expect, like fullerenes. So this is going ahead at the moment, and it's being supported actually by Extreme E, which is the electric car racing outfit in London. So just to say that the probability of being able to collect more and more black ice samples from the top of the Greenland ice sheet is something which is continuing.
Thank you, Peter. Actually, I've got one quick question for you, possibly both of you, before we finish. Jason Box gave a very lovely presentation at COP27, and he was describing and showing photographs of the black the black deposit. It looked like deposit in Greenland, but actually he said it was biological growth rather than actually black carbon as such. So it's to do with algae as a result of the sort of the warming conditions there. Would you care to comment on the contribution of that to the darkness over Greenland versus black carbon, Clive?
I think Peter would know more than me on that. I'm not an expert on it. I'm mainly here really to say that there's a tool that's available for making nanoparticle sized dust particles, and the cloud physics experts, they should know about that. Now, if they say making extra aerosol particles in the air is of no use to us whatsoever, then we'll stop talking about it. But we'd like to hear a response from them to say that it potentially might be useful for producing cloud cooling.
My question was,
I can't say anything about algae. I know that algae, just the same as others, and black carbon. We know that black carbon goes up in the stratosphere and it comes down in the polar regions as well. But quantifying it, we haven't quantified that. Others have, and there are papers on that.
Now, so Peter, my question was the source of the blackness over the Greenland. Jason was saying actually he felt it was algal growth rather than any deposit. That was my question.
No, I don't think it is. I think well, not mainly algal growth. The Raman spectral analysis we've done is showing mostly inorganic components there, so if it's organic, of course, where does it come from? If it's green, you're on top of the Greenland ice sheet. The nearest, in fact, the nearest source we've found is actually in brush fires in Sardinia, which is quite a long journey away.
That's an understatement. Right. I think it's now time to break for lunch. Very, very grateful to all of the people who've contributed this morning, presenters and questioners alike, not just the second session that I've been chairing, but also the first session that Hugh chaired. Thanks ever so much indeed. And now sort of further discourse over a meal. And we'll be back after lunch. And those of you who are online, we look forward to hopefully seeing you as well. Thanks ever so much.
Thank you.
We're about to start. Sev Clarke, live from Mount Macedon, I guess. Is that where you are, Sev?
That's right. That's right.
Excellent. Now we've got a question for you. At least Mike, our tech person, he's got your slides, but wants to know whether there's a timer on the slides. Do you want the timer on, or do you want to? So the slides will advance automatically according to a predetermined schedule. Are you happy with that?
Yep, that'd be fine. Yep, that'd be fine.
Okay.
I'm getting some feedback, Hugh. when I speak, it comes back to me a second or two later.
Well, Australia is a long way away. No,
I don't think that's the cause.
Why might Sev be getting some feedback? Is this microphone on? No. Can't think. Okay, so Mike is suggesting you turn your volume down, or turn your or plug in some headphones or something. So you
I don't have headphones.
Well,
That
if you
didn't
just
give
turn
feedback.
the volume on your. Okay, well, anyway, we're going to have to move on because everything's fine at this end. So
Okay.
I think it's
The feedback seemed to have
right,
stopped.
excellent. Well, we hope you only get. I mean, we're hoping the whole of today's session is only positive feedback. One of the great things about this subject of climate repair, geoengineering, whatever you might want to call it, is that there are various groups that have been meeting online globally, and there's a particular group on Monday nights. It's been really interesting getting to meet people and share ideas. And one of the people on that Monday evening or Tuesday morning for you there, Sev, has been Sev Clarke, and he's given us some neat ideas about ice thickening and other things. So Sev, without further ado, would you like to give us a rundown of what you're thinking about?
Sure. As there is much text in the following 4 slides, which you can read much faster than I can talk, I'll give you a time in silence to digest each slide before I make some quick comments on it, if that's okay. So
that's fine.
We turn to the first slide. Hugh, can you take the next slide?
Do I do that here, or is that done? Yeah, we've got the first slide, ice shield array.
Yeah, now next slide. The graphic.
Oh yeah, no, we were at the graphic, so we'll go back 1 slide then. Yeah, there's a graphic, ice shield array.
It's not.
We can't see the presenting mode online.
Ah. So
That's it. Yeah. Now take a minute just to look at that. Now, the first thing you should notice is the diagram has been compressed maximally horizontally. So the ice sheets are in fact much wider. They go to about nearly 3 kilometers in diameter and about 4 to 5 kilometers square in size. Each individual ice mountain is fused together with the others in a hexagonal close packed array with polynyas between them. And the good thing about it is that we can allow the Russians and the Americans to have their polar ice routes unencumbered and yet still freeze the Arctic using this method. Though it would help if we do the MCBs and the CTMIs and the FISTOPs and the other methods as well. This diagram also doesn't show that when you're getting the ice freezing and the warm air going up from it, that's actually producing a lot more moisture in the Arctic air, and therefore you'll be getting a lot of snow hitting those grey-black ice and snow fields, which Peter Wadham showed us. So that's another way of increasing the albedo on what's already there. And with any luck, it'd be thick enough snow that it'd last all year, and therefore we wouldn't see that grey black stuff again. Another thing this doesn't show is that the ice arrays are designed to actually ground themselves in much of the shallower seas, less than maybe 500 meters deep. So that's a way of making stable platforms on which you can do logistics experiments and have people doing work to harvest the methane and whatever. Okay, let's go to the next screen then, please. I'll give you a minute to read this. The main effects we're getting are an albedo enhancement from the ice shields. You're getting bright snowfall because of the brine falling off the ice shields, which is full of carbon dioxide and oxygen. You're getting some increase to the overturning currents, which are at the moment have been reducing, and we want to keep them strong. And you're getting those gases taken down to the benthic deeps, where the oxygen can help the biomass down there, and the CO2 can react with the seabed carbonates to produce long-lived and stable bicarbonate. You're also getting the methane and carbon dioxide emissions from the seabed. You're plugging the vents there, and whatever else is getting emitted, you'll be able to harvest and use for proper purposes. And finally, you're getting the ice and the transpired heat efficiently radiating energy out into space, which I reckon is pretty nice too. Next slide, please. Give you a minute for this. You'll have to be fast readers for the minute, I'm afraid. Okay. I see the 4 key things which are most important for academics and possible users to look at are the scalability of the technology, the risks it imposes, the costs or the cost effectiveness of it, and how can all these things be tested so that communities around the world can feel confident of giving it approval for gated tests, scaling up until we can get a full solution. So the first of these things is scalability. And because we're using the polar winds as our energy source, that's a pretty strong and permanent and sustainable form of energy. So all we've got to worry about really is how fast we can build these things and maintain them. It's also good because even with increasing temperatures in the Arctic, so long as the winter temperatures get to be 10 or 15 degrees below freezing, we'll still be able to use this method to increase the coverage of ice growing out from the shoreline towards the North Pole. Therefore, we've probably got 5 or 10 years in which we've got a window in which we can test and deploy this stuff to make it work. We're not all going to lose it as soon as as most of the summer ice goes. Provided there's some winter ice, we can still use this. I perceive the heaviest risks of this technology is in the Arctic environment itself and the Antarctic environments. They are particularly harsh environments, and the harshest bits about them, apart from the cold, are the risks of strong waves and strong currents to any infrastructure which you put up there. Provided we can get these ice shield arrays to be grounded, those heaviest risks can be mitigated. You'll still have strong winds, but if you're on a secure platform, that's something which you can handle and which the bases around the polar regions have been handling for the past 100 years or so. The risk of methane bombs is going to be an increasing one, but at least if we get more of them happening somewhere near where our infrastructure is, at least that methane rises in the air, unlike carbon dioxide, which could spread out over the environment and make things rather difficult for any hardy scientists up there. The risk of pumps freezing we can minimize by putting it in the relatively warm water and keeping it there, and by, when the pumps are intermittent, as they have to be for this method, you let the water drain back quickly so it doesn't freeze in the pipes. Turning to costs, those costs are substantial, but eventually I believe we'll actually be able to make putting those windmills, those wind turbines and satellite wind pumping stations into the Arctic regions. I think we should make them profitable. It'll depend a bit on whether you're getting any carbon credits or any negative radiation credits, but from the albedo enhancement itself, that is a public good which you're getting. Turning finally to testability, you're going to hear a lot more of this from our next speaker on what he's been able to do. And I'm suggesting a few more things of what we and the practitioners beyond us will need to do to test this thing to make sure it's safe and effective.
Sev, we need to be winding it now.
Yep. Turn to the next slide and I'll let people read that and we can go to questions right away. So Hugh, are you going to organise the questions?
I am organising questions. So
good.
Got a couple of questions here. So let's just first pass to Andrew Lockley here.
Hello. I'm interested about the viability of the technique in general, in that I just wanted to summarise the work of Madeleine Hoteling, who I don't think is at this conference online or in person, but she found that the effect of this method was dominant in winter, whereas albedo modification methods were dominant in summer, which is when you need the ice more, because that's where you get the reflectivity benefit. So is building up winter ice really the right solution?
Yes, because this winter ice is permanent ice. Once you build it up and maintain it a bit, it'll stay around virtually forever, provided you keep the maintenance going. It's not like simply making winter ice last another couple of months. Once you've got it out there, it stays.
Right, so I'm interested in you said.
Sorry, I can't hear you. Can you speak louder?
Is that better? Yep.
There are severe conditions in the Arctic, which there are. And one of my issues is, how do you create the oil companies have lost many oil rigs because they weren't ready for the sea. And the change in circulation, AMOC is likely to be badly affected. Have you included that in your calculations of construction of your ice domes? Because from the scientific point of view, that is a huge challenge, those two factors.
Yes, I have. And the answer is that you can grow ice up to 50 to 80 meters thick every winter season. So if you start growing your ice shields out from the shallow waters, gradually taking them into deeper waters, you can make sure that most of them, in the Arctic at any rate, are grounded securely so that currents do not affect you once it's grounded securely. In the Antarctic, it's a little bit different. You have to, because it's so deep, you won't be able to do that too easily. So you'll need to have basically floating platforms floating around the circumpolar current, getting thicker every year, but still remaining mobile.
And we have somebody by the name of anonymous attendee. Answer live. Do you want to ask your question? Is that possible to click the answer live button? There we go. You're live now.
I can't hear anyone.
I see. So the question is, how did we arrive at 2 centimeters per hour of ice thickening?
That's my guess, as you'll see in the last slide. I figure out if you use intermittent pumping, if you leave once you've had one gush, if you leave it for 10 to 15 minutes, if the air temperature is minus 25 Celsius, that surface ice will very quickly get down to very close to minus 25 again. And therefore, when the next gush comes, it will able to make a new bit of ice, a new level of ice, maybe a few centimeters before the next wait time and the next gush comes. I think that 2 centimeters per hour is probably a conservative estimate. I could quite see it as getting up to 6 or 7 centimeters an hour, but that's what some of the Cambridge researchers should be able to tell from experiments in their cold rooms and whatever. That's a key thing to measure, to see how fast we can make it, how fast we can thicken ice using this ice mountain area method. The previous freezing methods have used flooding ice, and that's terribly inefficient. That means you have to freeze all the brine too. My method, you freeze 80% of the water and the 20% of the brine falls back into the water. So you should be able to make ice far faster than in the flooding method.
So, well, that's great. We're going to leave it there. Sev, thank you very much. Big thank you to Sev.
Good day. See you.
And greetings to Mount Macedon from in the dark from sunny Cambridge. And go D's, by the way. So now we're on to Jacob Pantling and Lectern Laptop, I think is what we do. Jacob is another one of our final year undergraduate engineering students who just yesterday was released from the clutches of education, at least for the time being, planning to start a PhD in October, so you're not leaving it behind. Jacob, tell us about ice thickening.
Thanks, Hugh. So I've done a project this year on looking at the basics of the thermodynamics of what happens when water is flowing over the top of ice. So I'll run through this briefly because I don't think anybody needs reminding. So the ice has decreased in both extent and its thickness over the last 40 years. So the ice thickness as well as its extent closer. Is that better? Can you hear me now? So yeah, so the thickness and the extent of the ice has decreased. So that's obviously due to Arctic amplification, which is driven by the loss of Arctic ice, reducing the Arctic albedo, which then causes more heat to be absorbed, which then drives more ice loss. So here's a graphic showing probability of an ice-free summer, and with 2 degrees of warming by 2060, it's almost guaranteed that there's going to be an ice-free summer in the Arctic, according to that. So the proposed one proposed solution is the ice volcanoes. So pumping water on top of the ice, as it flows over the ice, it freezes, and that thickens the ice in the winter, and then it survives the summer, increases the albedo in the summer, and reflects more sunlight. That one. So moving on to my project. So I've done experiments and modeling of water flowing over the surface of ice, just in a simple, small experiment. So it was based on previous work done last year by another 4th-year project and by myself over the summer. And these were the results for water flowing over a channel down the ice. As you can see, they're not very reliable, and they don't match to the predictions that were made. So my project was aiming to develop a new theory that predicted the ice growth and to get repeatable experiments. So first I started off with the channel flow in the Trinity freezer, so where we just were earlier in their meat freezer, and you can see the setup there. So there's a pump in the background, the water flows it down the channel and then off into a collection bucket. So this video, if it plays. Okay, maybe not. That just shows the setup in a bit more detail. So here are my results for water flowing over a channel. So you can see this is the change in ice thickness with 0.5 degree water at the top and 0.8 degree water at the bottom. As you can see, where the water comes into the channel, it starts to melt the ice, and then further down, it thickens it. So you can just zoom in on that plot. So we've got 3 plots there. So there's a no thermal boundary layer assumption for an inviscid flow, which is the blue line. And there's the yellow line, which is a thermal boundary layer also in an inviscid flow. So they're both inviscid. And the green line, which is the new model, is the boundary layer in a slightly viscous shear flow. And as you can see, that matches to the data nicely. And the experimental data fits that model. So then for 2 degrees, the results weren't so nice, possibly due to some of the assumptions made in the model. So the heat conduction through the ice and the heat convection from the water to the ice were both assumed to take place at the original interface, so at that black line on the plot. As you can see, with the 2 degrees of water, there's a lot of melting. So that assumption is, I think, invalidated, and that's one of the reasons why it's not, it doesn't match the data. And also, the water pools where there's all that melting, so it's not flowing over the surface nicely. And then that's another assumption of the model, that there's a continuous flow of the surface, and that's not what observed. So then I moved on to radial experiments and radial flow. So I developed a model of the ice growth for the radial case, for the inviscid case, because viscous flows radiate outwards are quite complicated and have only really been done for very, very viscous flows, like something like honey, rather than water, which isn't as viscous. So here's the setup for the radial experiments. So I've got the water being injected from the top, flowing over the surface, and then it's measured using the micrometer you can see in the top photo. So these are the results from those experiments. So the 2 experiments will run with what I was aiming for, 1 degree water. I think the bottom line, the red data, is where the water was hotter, warmer, so it's melted more. As you can see, the top experiment matches to the predictions nicely. The yellow is the thermal boundary layer prediction, and the blue is the no thermal boundary layer prediction. And neither of them really captured the shape of the melting where the water was injected. So the water was injected with a water pipe which had a finite area, which was about the same order of magnitude as you can see that bowl shape. So it didn't match the models in that case because the models assumed that it was injected with a point source. But as you can see, the data in purple or further out, especially for the freezing, fits to the models nicely. So to conclude, so for the channel case, I got repeatable experiments for both 0.5 degree and 0.8 degree water, and they matched the new model for the thermal granulae in a slightly viscous flow. For the radial case, I got one set of experiments that matched and one didn't. I didn't have time to get a third set, but hopefully that would have matched up nicely to the purple experiment for the radial case. So for future work, well, there's obviously some implications for the ice volcanoes. If the water is above its freezing temperature, then there's going to be some melting where you start pumping it. And if you had an ice volcano and you wanted to pump it, then it's just going to melt a hole around itself, and then it's going to be useless. So you need to make sure that you don't get melting where you're actually pumping the water on if it is slightly warmer than the freezing temperature. And then some future work, you need to look at the behavior when using salt water. So I've used fresh water in all of my experiments, and the ice has no salt in it either. Combating the melting at the inlet, as I've discussed, including convection and to the air and radiation. So for these experiments, the dominant heat transfers were the conduction of heat through the ice and the convection of heat from the water to the ice. But obviously, convection to the air and radiation into space would be more important over longer timescales. Where that energy ends up will also be important, the impact to the climate system, the impact to local communities and wildlife, and how the new ice might behave differently to any ice that naturally forms on the bottom of the ice usually.
So, questions for Jacob. The usual suspects.
Very interesting. I was going to add one modification. I used to do this in the lab, not with a third-year project, not with moving ice. And the biggest factor was the temperature of the water that you want to freeze. Yeah. So warm water freezes much more rapidly than cold water. Now, we never did figure out why, but I think if you could control the temperature of the input water more, and I think you might get a better fit. But that's only a suggestion because I've battled with it for years and I got nowhere.
The issue that I had was I had thermocouples to measure the temperature of the water that was as it came out of the supply pipe, but the thermocouples were disturbing the water too much because it's only a very thin film. So I couldn't get an accurate temperature measurement, but I had an estimate I measured the temperature drop as it went through the pump and then took that and then measured the temperature in the water reservoir. And that was my estimate of the water temperature as it started flowing over the ice.
I mean, there's that sort of urban myth thing that if you want to make ice cubes and make them freeze quickly in your freezer, you fill the ice cube trays with warm water and it freezes quicker.
I wanted to ask two interlinked questions. So firstly, did you do any kind of video that would enable you to assess the albedo of the surface as the water's freezing? And secondly, have you considered the kind of microstructure of the ice and the flow channels when you are using salt? I know you've yet to use salt, but my concern is that you'll end up with brine sort of fingers and puddles, which will make weak spots in the ice and fundamentally change the physical properties and also the optical properties. But because you're not using salt water yet, you need to baseline what you're doing so that you can see these changes, right?
Yeah. So it's no longer up there, but so yeah, when the water's flowing over the surface, obviously the ice you're not longer seeing the clear surface of the ice. But if it's in the winter, then hopefully that wouldn't be an issue with regards to the albedo, because you wouldn't be pumping water over the surface in the summer when it's absorbing ice. And in terms of the salinity, first year ice, when it freezes, can be relatively salty anyway, and then the brine works its way out. So yeah, you'd obviously need to look at how salty the ice is and how that compares. But yeah, first year ice when it originally freezes isn't pure fresh ice, and the brine does work its way out of the the ice over a period of time.
And then we've got Marvin Chung online. Do you want to, perhaps if we click the answer live button over here, we can, Marvin's voice will come over magically, and nearly there. Yeah, we're coming there. Oh, I see. Oh, well, look, I'll ask the question. How would this intervention affect plants and animals on the surface or directly beneath the surface? I mean, we're kind of assuming that the ice there's no life, but maybe there is.
Yeah, so there is ice, there is animals that live in the cracks underneath the ice. And obviously there are things that live on the surface. I guess it's a question of, are there areas where we can implement it where there's minimal impact to that wildlife? And if not, you know, at what point, what impact are we willing to accept for the effect that we're going to have? So I guess it's a balancing act between how much ice we can generate in the location and the impact that it has on the local wildlife.
So, excellent. Thank you very much. Now, we've got a, before we move on to Tracy, we do have a guest intervention because Andrea Ceccolini is from Real Ice, has just got 5 minutes, if we can keep it nice and short.
I will keep it very short.
Just as a follow-up to Jacob's work, because he's been himself doing some stuff.
So Andrea Ceccolini from Real Ice. We are a startup. We are into the ice thickening business, so very consistent with the previous presentation. We are mostly UK based. This is our team. Our model is really to take the latest science and existing technology and then design and prototype re-icing devices, field test them and feed back into science. So we completed our first full cycle, including field testing last February in Alaska, in Nome, testing our first electric pump device, battery powered in that case, very successfully. I'll show you a couple of pictures if you want later. We are on to the second phase. We are prototyping a hydrogen fueled pump with a fuel cell, and we are planning to go to Cambridge Bay in Nunavut, Victoria, in November. And then we'll probably use either Nome in Alaska or Oulu in Finland for a February test. Our model, by the way, one of our advisors is online, Peter. I hope you're still there. He's been advising the company for the past year or two. Let me just jump to the science to make it quick. Our model is based on a paper from Cecilia Beetz and Andrew Pantling from the University of Washington. We found that this was the most advanced technique and method to re-ice, so to pump seawater from under the ice to above the ice. The method consists in flooding the snow layer on top of the ice, refreeze that layer to reduce the conductivity of the ice, and basically observe increase ice growth from the bottom of the ice, which is the natural way to grow the ice, instead of growing the ice, let's say, from the top. Basically, if you flood 20 centimeters of snow, you gain 70 centimeters of extra ice thickness. We've done our calculations for a large scale sort of re-icing. We know there's roughly 7 million square kilometers in the Arctic that could be addressed in terms of either preserving multi-year ice or restoring multi-year ice potentially with this method. So long term, we plan to go underwater with our devices for a number of reasons. We believe in a distributed model with very nimble, lightweight devices that would carry the water pumps as a payload. We would use green hydrogen, so no emissions. Once we produce it, obviously with renewable energy, ideally wind or even solar during the summer, but potentially other sort of ocean type energies. with a relatively small number of energy hubs, so we could drive a sort of large-scale restoration and preservation of sea ice. I'll let you read a little bit the notes in here. But basically, our second stage is about testing the hydrogen itself in cold conditions. So Cambridge Bay and the High Arctic Research Center from Canada is going to help us in that as we go there in November. And we plan to run a larger scale experiment. While last February in Nome, Alaska, we covered in a number of experiments every day 500 to 1,000 square meters in our tests. Here we plan to cover a few hectares and actually have a control area where we compare the impact of re-icing versus doing nothing in around the sort of Cambridge Bay area. I don't know, I've done the 5 minutes. I don't know if you want to maybe just start to take a few questions.
That'd be great. Thank you very much. So we may be time for a question or two and then moving on.
By the way, we've been studying a little bit. There was a question on impact on biodiversity, animals, etc. We believe growing ice from the bottom, like it happens naturally, preserves all the, let's say, the smaller scale animals that already sort of live in the ice. But also, we are discussing both with local populations and with the experts about other marine life, like seals, etc., that need sort of the presence of ice for their normal life.
Very good. Thank you very much.
Okay.
Great. Oh, we do have a question. Oh, we got a question. Oh, yes. Isabelle has a question. Hand up there. Good.
Yeah, thanks for bringing that up. I'd be curious to, oops, there's some echo. I'd be curious to learn more about the stakeholder engagement that you talked about. So how does that exactly work for this kind of project?
Yeah, very important point. First of all, I think contrary to what we heard from many other projects, we had a great reception in Alaska when we went to Nome. So we had local contacts and we selected Nome because we knew the people that could take us closer to the, let's say, indigenous population. But we had a great reception from local people to a point where we had the children, observe what we did locally. We were invited to a local school to speak and describe our project. And they took it very enthusiastically, like a positive message for climate. While many of the discussions they had about climate before were all doom and gloom, we gave them a little bit of hope with something that they can relate very easily. Thicken up ice in front of their coastal regions, save them from coastal erosion, give them a longer season for fishing, hunting, and traveling. So that was very simple. Now for Canada, because we'll go larger scale, the permitting is obviously more complex. And we are going through, first of all, we've been accepted by the CHARTS, the institution there, to conduct a research, but we are also going through the NRI, so the National Research Institute, and we'll go through the Hunters and Trappers Association locally to make sure that people understand what we're going to do and it is accepted by the local population. And if we want anything like this to work in the region, it has to be done through the indigenous population. So we are very much in favor of engaging properly and well ahead of time with this population. Now, I didn't say that our plan is over the next 3-4 years to get to a point where we scale the technology enough, we test the underwater devices so we can refreeze a bay in the Arctic, like a small bay, and that would show the scalability and take us to a point where we can engage with larger manufacturing for actually scaling the building of devices and with renewable energy producers, which obviously it is a high energy and energy intensive project, as you can imagine, given the large areas. But yeah, engagement with local population is essential to even get started.
Can I ask a follow-up question?
Thank you very much. Okay, yeah.
So
yes, go ahead.
That sounds really interesting. I was just wondering about larger scale impacts, right? Because if you think about re-icing larger areas, that will have impacts on the climate system as well. So it would also have like a larger political dimension, right? So you would also need to engage with other researchers, politicians, citizens, right? Is that something that you have considered?
Absolutely. Part of, and I think we're going to hear a lot about that probably in the next sessions, and I'm not the expert, but definitely a project like this, if anything, not just for permits and agreeing with counties, but even just the funding part of the projects will need quite extensive engagement with institutions at that level. So that the cross organizational, sovereign, but also individual countries. We're not in the best time in terms of geopolitics for that, but again, we found quite a good reception from these people we spoke with in terms of what the future could hold for this type of, I mean, people are realizing that we need this type of projects going forward to resolve the climate problem. So we're confident within the next 3-4 years, once we are ready to show scalability, there will be more awareness and hopefully get to have those discussions with Arctic Council and other institutions.
Great. Well, thank you very much. And yes, thanks again.
Thank you.
And now, Tracy, we're moving on to the area of law, ethics, governance. Now, are you?
No problem.
Perfect. That's just what we need at this time of day. So let me just link that off there. Good. Tracy's based at the University of Houston, Texas, well, it's great to have you along, and be very interested to hear what your perspectives are on the legal side of things.
Great, thank you. And good afternoon, everyone. Can you hear me? Yeah. Thank you for sticking through to the very end. So much appreciate your perseverance and stamina. I'm Tracy Hester from the University of Houston Law Center, where I teach environmental law. I also teach a class on climate intervention law, which I've taught now for about 6 years, and have tried to focus on some of the issues I'll talk about with you today, namely what sort of governance frameworks, what sort of legal requirements might apply when you're actually trying to do field deployment or larger scale implementation of some of the research that you've been doing. With that in mind, I do want to begin with a small confession in that I'm flying a slightly false flag here. You may notice that the agenda lists me as speaking about, if I remember correctly, ethics and governance in the law. And I'm not going to focus on the governance and ethics from a theoretical perspective, as probably, to the degree I should. With the time we have, we probably can't get into it. I'm happy to talk about that with you in the questions and answers afterwards. But my sense has been that debate has tended to be locked in a repetitive cycle, and that it hasn't really enabled or translated into effective results for researchers who are trying to do things on the ground. So what I'd like to talk with you today is instead a more operationally focused question, which is, if you were to approach a lawyer and ask what sort of legal requirements do you have to comply with to actually do refreezing the Arctic on any kind of scale project, what sorts of issues do you need to consider? How would they apply? So as always, if you were to ask me that question, the answer you'll get from any lawyer or law professor will be, it depends, which I know drives people crazy, but it opens the door. And what I'd suggest to you is that there are sort of 2 precepts which will help us. And by the way, I apologize, I don't have a PowerPoint. We're back into the pre-technological dark ages here, but I was hoping that I could wave my hands a lot and substitute for a PowerPoint with you. So 2 precepts. The first precept is the idea that there is no explicit regulatory framework that governs any kind of climate intervention. We do not have a climate intervention statute or law on either the international or domestic level. I can talk about some attempts to interpolate climate intervention requirements built into other existing treaties that were written for other purposes, such as the London Protocol or the Convention for Biological Diversity. But we don't have anything specifically crafted for the issues posed by this kind of research. Same on the domestic level. We're extending existing legal frameworks written for other purposes to cover this kind of work. So with those precepts in mind, the second precept is the idea is, if I say it depends, what does it depend on? I mean, what are the facts that matter? And what I suggest to you is that there are really two intersecting themes you need to look at. The first is, where is it going to take place? The most fundamental determinant of what laws you're going to have to navigate are, is one, if it's on land or if it's on sea. And then the second theme that intersects with that is it international law or domestic law? What level of law are you engaging? And so if we had a whiteboard here, at this point, I'd go over there, and I'm sure all of you have tortured students like this in the same sort of way. I'd put up a 4-quadrant table. And if you could imagine in your minds, if you would, land and sea as your rows, and international and domestic laws as your columns, and imagine which quadrants we're talking about. So the first intersection is land and international law. And in that respect, there's an enormous amount of what I'll call customary international law that is developed for other reasons that could apply to this kind of research, for refreezing the Arctic, for mooring glaciers, for other types of things that physically harmonize with the environment. In that context, I'm sorry? I was going to say, I teach in law school, so I'm used to being interrupted by students all the time. It actually makes it more interesting. So if you have a question, you want to ask anything in the meantime, please. Okay. So land, international law, customary international legal principles. The first and most important is that no nation can allow its sovereign territory to be used in such a way that it causes harm to other nations outside its borders. Transboundary impacts. This is the one I'm sure many of you have heard about other contexts. The Trail Smelter decision, it's been embodied in other, particularly the Rio Convention, the Stockholm Convention. The idea is that you can't allow your nation's territory to be used in such a way that emissions or impacts cross the boundary and harm another nation. That is one of the most fundamental concepts of customary international law. It has been elaborated and extended so that the idea is that because of that kernel, that core concept, it also imposes a duty on nations to do environmental impact assessments before they do any kind of scale activity that has this transboundary impact. So in that regard, imagine, if you will, the Arctic. We have areas where you might be doing work that's going to be based on land. And in that regard, if you're doing things, because remember, as the lines converge towards the North Pole, the physical dimensions and distances that have to be traversed may result in your having much more readily determinable transboundary impacts than you would if you were doing something in the lower latitude. So that seems to be one of the first principles that nations will have to engage with. I can talk about how which nations determine which borders extend into the polar region. But I also fear that this audience is deeply familiar with those concepts already. My deepest fear as a professor is I tell people things they already know. All right. So with that in mind, we can sort of talk about the baseline method. Essentially, you extend boundaries up northwards. So you end up with slices in the Arctic where Russia controls the largest portion of it, but obviously then have similar positions for Canada, for Norway, for the United States, for Alaska. Yes.
What constitutes harm to another country? You might explain that. Right.
No, it's a valid question because normally the question answers itself.
So can you repeat the question because online wouldn't have heard it?
For those online, the question was, what is harm? How do you determine what impact constitutes a harm? And under international legal principles, the question typically answers itself. Usually every case you've looked to deals with something that is readily identifiable as pollution or other type of impact. So there's never been an engagement as to whether or not there is a harm based on a benefits detriment calculation. We have a different situation where if you're actually trying to restore a pre-existing condition and it's in such a way that it mitigates future larger harms, what may be viewed as a short-term impact to an adjoining nation, which may be, from that nation's perspective, harmful, may be in a larger perspective actually not pollution. And that is something we've not engaged with yet. I suspect it's going to be answered in the way I think I'd expect court would normally answer it, which is they don't care about the big picture as much as what is the person who claims injury can point to that's concrete and immediate. And then it's up to the person who's inflicting that impact
to say, I have enough benefit from this that it compensates for that injury. And you have to make sure they're made whole. But that process is going to be very tricky in the Arctic. It's an excellent question. Thank you. So I'm only one quadrant in. How much time do I have left?
You're about 4/4 into your allotted time.
Oh, wait, that's not fair.
3/4.
3/4. Okay. Then if you would, land international law, I've described to you customary international law principles. Land domestic law is where the action will most likely be. For example, if you're doing it in Alaska and you're doing any kind of ice thickening or activity that's going to have an immediate land-based impact, you're going to be dealing with multiple different environmental statutes that already apply, even though they're not written to govern climate interventions. So as a result, you'll need to navigate the Endangered Species Act. You're going to need to navigate the Clean Water Act if you're doing anything that might be impacting an aquatic-based system, despite a recent decision from the Supreme Court last week. You're going to be dealing with the National Weather Modification Act, to the extent that you're putting anything into the air or onto the land that's designed to alter weather. It's a statute that was written in the United States in 1972, designed for other purposes, but it clearly by its text is going to apply to weather modification activities that are designed for climate intervention purposes. And it essentially mandates a prior notification requirement to the federal government. You'll have to deal with the National Environmental Policy Act and doing environmental impact statements. And I can talk about what the triggers are for those. That's row one. Row two, ocean-based, international law. Here, I'm just going to tick them off quickly, going by. The United Nations Convention on Law of the Sea is going to be the main framework that's going to govern activities in the Arctic, because obviously there's no land. So as a result, essentially, governance of any environmental impact is going to be under Law of the Sea conventions. That has several consequences. How far you are away from shore is going to matter. If you're within territorial waters or the exclusive economic zone or on the high seas, you're going to have restrictions that a nation can impose on the free navigation of other nations. So the UN Convention on Law of the Sea actually has provisions on building artificial islands. Well, if you're refreezing portions of the Arctic in such a way that it's impeding navigational zones, as we saw with some of our prior discussions, that may be deemed to be a violation of international law if it impedes with existing traditional routes of navigation. If it's a new route of navigation, it's a different question. Yes. Please.
No, just microphone.
So you said that impeding navigation might be considered to be a harm or otherwise impeding on the rights of a nation, right? But the Arctic has melted and that's resulted in a loss of multi-year ice and sometimes channels opening up, right? So do the nation's rights to navigation, are they pegged to pre-industrial or are they pegged to climate prior to intervention? Because I think you can make a pretty good argument that you're just restoring what nature had in mind and therefore you're not impeding anything and they should go away and stop complaining. But your interpretation appears to be that what happened last week should continue this week.
Well, first, Andrew, thank you. But I have to say, that's not my interpretation. I want to be, you listened with a keen ear. What I was describing was the Law of the Convention provisions that deal with artificial islands. And it specifically in the convention itself says that you can't build an artificial island that impedes traditional paths of navigation. That doesn't apply to the right of free passage or innocent passage. In that regard, you may have an answer where something that is new and created is going to not trigger the same protections if you're talking about building an artificial island, as opposed to just impeding navigation by creating an ice shelf. And admittedly, this is all brand new. We don't have any clarifications from any international jurisprudential bodies yet.
I'll just give you just another minute. Yeah.
Okay.
Because we ought to be winding up and moving on.
I'm on the fourth quadrant anyway. So fourth quadrant, which was, remember, is now ocean domestic. And here it's going to be things that are, again, exist already and laws written for the purposes. In the United States, it'd be the Ocean Dumping Act. It'd be the Marine Mammal Protection Act. All written for different purposes, but all clearly extendable
to the concepts we're talking about here. And I can talk about that permitting and review process. So in parting, a couple of thoughts to take away, questions to consider, maybe we can discuss in the next session. One, all the international law concepts I talked about with you are designed to apply to nations, not people. To a certain extent, you as individual scientists do not need to comply with the law of the sea, but the nations that you're operating under the approval of have to assure indirectly that you do. So to a certain extent, you have a sort of two-bank shot you need to worry about. Number two, this doesn't talk about liability, litigation. There are lawsuits being filed around the world now, 28 different courts in the United States. We have lawsuits in Italy, France, Britain, all targeting large-scale energy producers for climate change liability. Those could set precepts that might apply to other future instances where someone alleges that a climate intervention project has damaged them. So to a certain extent, we need to watch that storm front and make sure that there's nothing that could be extendable to work written and done for wholly different purposes. And I have a list of about 20 other questions, which I'll save for later, but I'm glad to talk about with any of you. Thank you so much.
So I guess we've got to be careful what we wish for. So, well, look, I think we're all getting to the end of a really interesting day. But what I'd like to do is to ask Robert and Woulter to come and take a chair on the stage. I don't know whether Mark can get three of us in shot, if that's possible. So I'm just trying to keep things more or less here. And I just see, by the way, that there are some questions. You're going to take a seat there. I'm going to stand up here, and I'll be able to. No, the other. Where's that mic that Antoinette had? Today's been an interesting day. Robert, what have you got? Where do you stand on? Sorry. Where do you stand on things that we've been talking about today? It's on, yeah.
Well, it's been really quite heartening because there's just again proves that there are so many people thinking and working hard on so many great ideas about how to address the issues that confront us. And you know, if it weren't for the students that are kind of coming into this afresh, and for the older folk that have been working on it for decades, really dedicated themselves to this task, we would be in a very much more serious condition. So however much of a problem climate change is, you know, we all have a huge debt of gratitude to this bunch of people and their counterparts elsewhere in the world.
And you're optimistic?
I am. I'm always optimistic. Optimism is a strange beast. So I have great faith in the indomitable spirit of humanity. So I always think that things are going to improve, but I don't believe that improvement will be monotonic. So there are going to be some ups and downs, and some of the downs might be quite deep downs en route. And that is, of course, for the future to tell us. So I don't think that I'm not sanguine that we are going to traverse these difficulties that confront us now in a what the economists would call a Pareto optimal way, which is that some people benefit and no one suffers. This is, to mix my metaphors, it's an omelette that we're not going to make without breaking some eggs, and we need to bite that bullet.
So, Woulter, what have you taken away from today so far?
I was invited by you to talk about my experience with my works for 50 years in the Club of Rome, which was about the bridge between alarms and paradigm shifts and political acceptance. And that's a different business. It's a different job. It's very different from what you do. And I, 15 years ago, when the first time I saw the spraying vessels by Stephen Salter, I said to myself and my friends in IPCC and the Club of Rome, this is a next step. It's an enormous paradigm shift.
let's try it. For 15 years, it was not possible to raise the alarm within the circles where I act, which is the World Community of Sustainability, the World Sustainable Finance World, Brussels, together with Hans van der Loo here in the room, intervening, lobbying, telling, and so on. And what's the missing point? One is, I hear many different opinions. If you want to be influential, that's not the proper job, the proper story. There has to be one story. Limits to growth was one story. If the politicians or the decision makers are to be confronted with an array of 10, 20 different opinions, they will not act because that's too difficult. Science, one day from the scrimmage, I've seen a scrimmage today, but a friendly one. One day from the scrimmage, then there will be one game coming out of it. Opposition and inquisition. I heard the word, who used the word inquisition?
Spanish Inquisition.
Yeah.
That was Andrew Lockley.
Inquisition. The inquisition and opposition is always there. Every paradigm shift that we have seen over the last 50 years goes with opposition and scandalizing and so on. You'll remember the attacks of the tobacco industry against their critics. The book of that, The Merchants of Doubt. So there was a paradigm shift, smoking is dangerous. They attacked the medical world for 25 years with an organized campaign costing hundreds of millions. Hundreds of millions. If we don't unite and make one story, the same will happen here. And I tell you how. There is a deep ecology. David King, the first time when we met, he said, can you talk to the deep ecologists in the world? And he said, take the train, go to Berlin. There's the Heinrich Böll Stiftung, which is the Science Bureau of the Greens, and talk to them. I said, no, Dave, that's not possible. Go to the president of Europe. We don't have a president of Europe. Go and talk to him. What you need is something very different, because you have to understand that not climate change is the only thing, but the people who defend the planet against interventions of this kind are all a function of an eternal dream of purity. That's where the word sin comes from. That's why there is guilt in the world that people experience. That's why there is virginity. And the escape always from those who say you are a group of sins. Islam people who say it about us, the Christians say it about it. All of them accuse each other of being sinful, of being blamed for the fact that the world is not pure, the world is not ideal, the world is not a paradise. And there are escapes to that. One is culprits. If there is sin, if there's trouble, there must be culprits. And that we have seen in 1930. There must be culprits somewhere. And there must be victims. So when talking to the young climate associations in Europe, they all talk about culprits and victims. And they are the ones who are the victims. Politicians must react to that. There is always an imbalance between what is needed and what business and finance can understand. How do they take decisions? That's what you should know. If you don't know how they take decisions, then this will not succeed. First of all, decisions are taken by denial. Denial is a fantastic instrument. About 25 years ago, there was a famous article in the Wall Street Journal saying it's not economic to save the planet. How could they excuse themselves by denial? If the problem is not there, then it's not necessary to save it. So that's the first one. The second was pressed by interest groups. And most of people here in this room, I've heard, what do you think of the fossil fuel lobby? I said, I know them. I know the stupids, those who understand, but most of them are normal, ordinary people defending their normal interest. They are not the culprits, but there are interest groups out of their own paradigms. And always the dominant groups win. How can you organize to become a dominant group yourself? The third one is an alliance. Create alliances. I was involved in the beginning of the environmental movement. Friends of the Earth, Greenpeace, Club of Rome, World Wildlife Fund. I was always there as a young science editor in Dutch television, trying to bridge communications and public with information and science. There is now an alliance in the world about from the side of the defenders of the purity. And they accuse us of playing God. And that's a very strong argument. We are playing God. And we are therefore part of Satan. So please, Satan, it's funny the way you approach it, but most people don't understand the humor of it. We do, and we love it. But at the same time, you have to find ways out of these three decision systems: denial, interest groups, and an alliance. And the alliance is what is needed, because if you don't, then in the end, the populists will take over. Hans van der Loo and I were visiting one of the DGs in Brussels last week. As you know, the Director General there is the top of the power. There are 31 Director Generals, and the one who is in charge of innovation and research, we had a 2-hour meeting with him. He said it's a fantastic story. But political power is to come to me and the Commission by means of alliances and groups and whatever. In Brussels, there's something like 10,000 different associations, alliances, who all combine interest. And they combine it and they are together. They are a troop. They are an army. And we are not. The NGO world, the environmental world is, but the climate repair people, 100, 200, 300 people in the world, including the politicians, is not an alliance. All recent paradigm shifts were organized in terms of political power by alliances, Greenpeace, World Wildlife Fund, and 1,000 others. So unless we organize the combination of science, 33%, implementation, 33%, and organizing influence, 33%, we will not succeed. Thank you.
Robert, would you like to follow that?
Well, well, exactly. I have since I got into this whole subject area, some 15 years or so ago, maybe a bit longer. Yes, thank you. I very quickly realized that there was a problem that needed to be solved, and that solar radiation management in one form or another, and at that time it was almost only stratospheric aerosol injection that was discussed, that this was an option out there. And my immediate reaction was, that is never going to happen. And it's not going to happen, my thinking then was, for the reasons that that Tracy gave earlier on, because if you're going to do any kind of solar radiation management at climatically significant scale in the global commons, it is inevitably going to have transborder impacts. And I have my working life before I got involved in this was in commerce, and I've had enough experience with lawyers to know that once they get their opportunity to get their teeth into that subject, it'll completely die a death, because the only people that will make money out of it will be the lawyers. They will have a field day because it is a total minefield. And I think the points that Tracy was making really need to be taken on board here, because it's one thing talking about modest little experiments in a laboratory. It's even another thing talking about slightly larger experiments in the field, like Scopex and SPICE and so on, and what Andrew was doing and what Make Sunsets were doing. It is a totally different thing to talk about doing those at scale, at climatically significant scale. And getting to that point, I think, is something that the international community is going to really struggle with. And I think the point that Woulter is making now, that we need to focus as much on the enabling infrastructure for these technologies as on the technologies themselves, is absolutely critical. Because otherwise, what's going to happen is we're going to get to a situation where the demand for these technologies grows and grows and grows because the climate problems become worse and worse and worse. And the technologies will be kind of progressing slowly-ish, but getting more sophisticated and more viable. But we will not yet at that stage have engaged in the discussions necessary at an international scale to implement them. And so we're going to have another delay whilst that whole process goes on. And one of my current mantras, taking from adages which you will all recognize, is that climate change waits for no man or woman, and if we want to be really diverse, or any other gender. So I think that there are really big issues in here. I think the point that Woulter's making about having a kind of a joined up approach to this is absolutely critical. It's not just about the technology. That's one part of the process. It's not just about I won't repeat what Woulter was saying, but I mean, all of these things are absolutely necessary. And picking up on Hugh's point about the three-legged stool, I want to make just to develop that in slightly tangentially. There's been one of the big objections to solar radiation management comes from the NGO community, from indigenous peoples and various other folk, who say they raise this moral hazard argument, which essentially says that we shouldn't do these things because it will take the fossil fuel companies off the hook, and it will take the pressure generally off politicians to reduce emissions because we'll have these alternative technologies. We'll have these alternative technologies to do these things. Now, moral hazard is something that kind of really I get very excited about, very uptight about, I should say, because moral hazard, without going into a lot of complicated stuff here, moral hazard is essentially an issue that arises where you have alternatives. You have choices to make. I could do this or I could do that. It does not apply where you have multiple actions, all of which are necessary. And here we get into this critical point, which I think is too often not appreciated, that we need to be clear about the distinction between necessary and sufficient. So this whole day has been about solar radiation management and albedo enhancement and so on. But we have got the traditional conventional approaches to climate change have been emissions abatement. Now, the discussion we've had here today doesn't make emissions abatement any less important. It doesn't make it any less critical. It doesn't make it any less urgent. It is necessary. And similarly, alongside that, you've got all the different forms of carbon dioxide removal, which have been referred to today on occasions, and other greenhouse gases as well. There's been some comments about methane and so on. Again, these are becoming, because the situation is becoming more severe, the climate situation is becoming more severe, these are also now necessary. Now, unfortunately, because of lack of decisive action over the last few decades, we now have a situation where perhaps if the international community had acted decisively in 1990, emissions abatement would have been sufficient. I mean, in the first assessment report from the IPCC, they were talking about reducing emissions to get back to 1985 levels. That would have required, you're going to like this, it would have required a reduction of 10 gigatons of carbon dioxide per annum by 2050. Well, that's nothing. Now we're talking about having to reduce it 40 gigatons in 30 years. So it's twice as much in half the time. So, our lack of action has just made the mountain higher, the challenge more difficult. So with each year as it passes and our lack of decisive action, the interventions, the solutions themselves, by definition, have to become more severe, more draconian, more risky. And of course, as they become more risky, we think, oh my gosh, wait a minute, there's extra risk there. I need to think about that risk. But we don't we too quickly forget about considering the risk of not acting. So you need to constantly think about the risk-risk ratio here. It is not just a case of we shouldn't do solar radiation management because it entails all these risks and these transborder issues and so on and so forth. What about the risk of not doing it? So we've created a situation through lack of action over the decades where now, sadly, and it is for me genuinely very sadly, some form of solar radiation management is also now necessary, because the other things, while still being necessary, are no longer sufficient. And if solar radiation management is also now necessary, the whole moral hazard argument disappears, because it's not an alternative. It's a both and, not a this or. So please do not, if you are out there listening to this and you are somebody that might be moved by the moral hazard argument, please put it back in its box where it belongs. It does not apply here. And sadly, we do now have to recognize that solar radiation management in some form is necessary. We've had really interesting talks today about several different approaches. None of them is in a fit state for deployment, or even in some cases for field testing. But we now need to focus our efforts, much the way that Woulter was describing before, so bring those technologies forward so that at the earliest opportunity, we can start to implement them at scale and safely to reduce the overall climate risk. That was my response.
Very good. Thank you, Robert. Now, Leon has very patiently been holding his hand up. If you unmute, you should be able to speak, Leon.
Hi. Can you hear me?
Yeah, we can hear you.
Yeah, I had a legal question, or a question about the legalities, because from shipping, we've been emitting, of course, a lot of sulfur already in the past century, which has been cooling the climate. But of course, that was not intentional. But now we've reduced in 2020 the sulfur emissions over the oceans by 80%, which is rapidly increasing the warming. So I imagine that maybe in the next years, when the effects become more clear, especially with El Nino now developing, some countries or some parties might consider again increasing the sulfur emissions. So I was wondering, like, what does this mean for the legality of intentional cooling versus unintentional cooling the climate?
There we go. Hi, this is Tracy. I assumed that was directed at me.
Yes.
Yeah. Yes. There's been a lot of commentary on the irony of the IMO's reduction of sulfur and bunker fuel causing essentially a mini termination shock. And there's been some discussion informally about whether or not there needs to be some sort of counterbalance to it. But I think it's been pretty clear from all the stakeholders so far that given the other health impacts of sulfur dioxide emissions at tropospheric low levels and other contaminants that are in bunker fuel, which is the dirtiest fuel you can possibly imagine in terms of contaminants, that it's unlikely they're going to roll back those SO2 standards for climate purposes. But I wouldn't be surprised if there was talk of additives that might increase particulates that wouldn't have a health impact, that you could modify the fuel standards that way. But given the way the IMO works, that's probably a process of years, if not decades. Does that answer that for you?
In some way, I think you mentioned that there's that the legality of intentionally emitting or intentionally cooling the climate, right? But now, in a way, we are also intentionally decreasing these emissions. So in a way, we are intentionally causing more rapid warming. And then just to mention so of course there's health effects associated with emitting these particles, but there's also research showing that if you would emit those aerosols, those sulfates, further away from coast, from the coast, the health effects will be quite small. So you could, for example, decide to have these scrubbers only working when they are near the coast, or have to use low sulfur fuel near the coast and high sulfur fuel further away from the coast. So there's of course ways to go about it. And again, I understand that IMO, those decisions take decades, or about a decade. But of course, if the effects become more clear, those decisions can be made much faster.
I'll agree, but I'm not sure I can offer a legal comment as much as a practical one. That it took an enormous lift to get the fuel emission standards reduced. And there's literally been billions of dollars of money spent to refit refineries to produce the ultra low sulfur fuel that they're using for shipping now. It would be a political firestorm in the United States and the EU to try and go and roll back those pollution control standards for climate-based impacts, even if you could make an argument about the health impacts. So having said that, I think you make a valid technical argument. I just think that the way the weight forces have lined up, it's going to be very difficult to roll those standards back.
Robert,
thank you.
I think it's been a really productive day, and I'd just like to comment on the ethical framework that is raised here, because one of the big anomalies that we see in the current climate paradigm, to use Woulter's term, is that the debate around ethics is really very confused, because if we look at the major ethical problems that are facing the climate, I would say the big problems that we see are things like extreme weather, sea level rise, biodiversity loss, and systemic imbalances. And those are all things which can be directly mitigated by albedo enhancement, but which really can't be mitigated by anything that we do for carbon. Carbon is just too slow, it's too small, it's too contested. And so the idea that we're going to fix the climate without enhancing albedo is simply absurd. So it's, no, it's not a question, it's a comment. So the situation is that we face a planetary security situation where the ability of the climate community to engage on security really needs new governance arrangements. It needs an ability to broaden the conversation about albedo to much broader constituencies than it currently achieves. I really hope that the Cambridge Centre will be able to pick up on this strategic vision around albedo. As Uta said, the science is just a third of the work, and really it's this strategic, ethical, political debate that needs to be joined much more.
So, Shaun, why don't you pick up on that very question from there?
So actually, I am going to share just a couple of things. In terms of the acceptability or unacceptability of some of the things that we've been talking about today, for example, stratospheric aerosol injection and the release of a foreign substance for the intent of, for example, increasing albedo. But if we just say reducing the impact that we as mankind are having on this planet. So let's consider aeroplanes. So there is a lot of work going on at the moment in Cambridge and elsewhere looking at how we might reduce the impact of flight. And the impact of flight on the climate. There are three big levers. Actually, the biggest lever, as I'm told, is to do with the formation of contrails. So in terms of the global warming impact that a few aeroplanes might have, and it's not just those little contrails that then form and disappear out the back of a plane. Some of them apparently can lead to the formation of cloud banks. But this is, lever number one. What's interesting is that the metric that's currently used in all of these discussions is this global warming potential, which is effectively the integral of the impact over time. So with contrails, it's a very big hit in a short time frame, and then you look at basically very little impact over the next 100 years, and then you divide it over 100 years, and you then compare that with other climate forcings as well. So if you actually care about the climate impact in 100 years' time, then interestingly, global warming potential is questionable as to whether that's the right metric. But anyway, we've got lever number one, which is contrails. Lever number two, of course, is the carbon dioxide emitted from this. What's lever number three? Water. No, that's to do with the contrails. Lever number three is actually the sulfur dioxide that's coming out the back end of an aeroplane. And in fact, it actually contributes to cooling. And there is a whole body of work right now, which is looking at how do you reduce the impact of flight on the climate. And, there's a research program right now, which is looking at changing the trajectory, changing the altitude which aeroplanes fly to reduce the likelihood, for example, of contrails forming. What is not being considered right now is changing the fuel mixture. This is my knowledge. And perhaps increasing the level of sulfur content, right? Now, it's a smaller lever, but would that be acceptable in terms of reducing the negative impact of flight? So the framing and the narrative is extremely important regarding the acceptability or unacceptability of things like geoengineering. So when taken in isolation, or sulfur dioxide being released into the stratosphere, actually that does focus the mind, and it's important that we get our heads around that. The second thing I wanted to share with you is some recent research that was undertaken by a gentleman called Ramit Debnath. It was published in February of this year. And it was looking at the basically the attitudes towards this term, like it or not, I don't like it myself, geoengineering. And the research was undertaken by the examination of about 13 years worth of Twitter data, looking at hashtag geoengineering. And the reason why this research was undertaken was that there are a number of voices that are quite vocal, quite loud, that are quite negative about this whole area of geoengineering. And the question that we posed was very simple, which was, we wonder what else those people who are commenting in this space are talking about. And I would urge you to, do a Google search on this paper. So Ramit Debnath is the first author. It was published in iScience. And you probably want to just use two keywords, geoengineering, and maybe three words, conspiracy theories. But what we found is that there's a very high correlation with the voices that are expressing negative views towards geoengineering, and those voices also commenting on things like the anti-vaxxers, the Trumps, the conspiracy theories. And what we find is that there's actually quite a degree of spillover from one, I would say one community. When I mean that, I mean a discussion community with the other. And the purpose of the research was really just to go and cast a light and just be transparent as to what those voices are also commenting on, for others to then judge and to think about the credence that they might place upon the different voices within the community. And we have a current working hypothesis that perhaps, and remember, this is just Twitter data, so it's one little echo chamber, it's a very narrow prism really into what really is going on in the world. But is it a vocal minority expressing very strong concerns, and where is the silent majority, and where are their attitudes? I don't know the answer. We don't know the answer, but I think there's quite a lot of work that needs to be done in furthering our understanding of society's views towards some of the things we've been talking about. Before we even talk about public engagement, actually, it's us who've got to do a lot of learning at the moment, hence the research side, to understand actually what's the baseline, what's the starting point, where people think about this. So I just wanted to share that with you. If you've got any responses, comments, yes, Andrew. Should we get a microphone to Andrew?
Well, that's
Well, thank you both, Shaun, and you, by the way, for a very enlightening afternoon. I think a lot of very valuable things have been said. And just to latch on what you just said, Shaun, I know that David King knows a fellow South African by the name of Auret van Heerden, whom I know. He's been living in what do you call the ballingschap, he's been expanded exam. And he has set up something that's called deep listening on the internet. And I wrote down an extra point, so I'll check both with you and her, that he is working primarily on what is happening with democracy. But I think it would be relatively easy for them to also put in different hashtags like you just suggested. I'm not a scientist. I work a lot with scientists, and I really enjoyed it, particularly if there's scientists like you, inviting such fantastic premises. But they're huge communities who have an interest in these topics, but are completely unaware of what you do. I think about coastal communities. I think about the City 40. I think about the Regional 100. I think about NATO. I think about parliaments. And I think it's very important, and Woulter has indeed indicated that already, that we bring that together. And indeed, what you said, had we done all this, at the Earth Summit 1992, the challenge would have been far less big. Right now, what we have is a flawed COP process. They're trying to open a very big door with 3 locks to a future with less than 1.5 degrees climate warming. Now, those 3 locks are supply side solutions, demand side solutions, and nature-based solutions. But they've been trying for 27 years to open the door with the key of 1 lock only. So that is why we've gone so much too far, that you're absolutely right. Treating the cause alone is no longer sufficient. So we need to treat the cause and to treat the symptoms. And the way I always put that, of course, if that does not happen, then this work will not save it either. It's and, as you said. The way I put it to these people that work on the mitigation adaptation only on the carbon part, I say, you have to do what you do. But even if what you do in the most successful way, the best possible outcome is operation successful, patient died. And so I think I just want to thank everyone here. This is incredibly important what you do. But I was surprised myself when a couple of years ago I heard about this. And today several of you showed slides about Toomey and Latham, and they did their discoveries in the 70s. We are now half a century later in another century. And so I also learned that this is a very beautiful town, but it's also an ivory tower. So I think what is really important that we build is straddle the bridges, towards community and the political decision makings. Last week, Woulter and I, we were at a conference in Amsterdam, and I actually in the afternoon did a talk about MCB as a potential solution. And actually, I can see his name, Fonger Ipma, he was there. And I asked him, has any of you ever heard about solar radiation modification? And these were not people that, this was a particular conference. None of them. And I think that is a big onus on all of us, and we need to help you. You also are not a scientist out there. I enjoyed meeting you over there. It is really, really important that we do this together. In Africa, there's a saying, if you want to go fast, you go alone. But if you're going to go far, you go together. And I hope that will be the outcome of this afternoon.
Okay, Andrew, can we get the microphone to Andrew?
We've got a couple of questions from Martin in there.
Yeah, I don't do comments, but this is just a comment. You said about the idea of enhancing sulfur and jet fuels. So just to let people know, I've got a submitted paper on that. That's the basis of the chemtrails project, to try and work out whether we can get aircraft that have enough sulfur in their jet exhaust and fly high enough to do so, either stratospheric aerosol injection or potentially, if we can't do that, marine cloud brightening.
We look forward to reading it, Andrew. Thank you.
A very quick comment, really. You talked about the changes in fuel oil in ships, but there's many more in India, for example. They're reducing the amount of sulfur emissions. You're talking about greening household gas emissions. So I think in the next 5 years, you're going to see a rapid growth of temperatures, extreme temperatures. And we've talked about mean temperatures. As a meteorologist, I'm not worried about mean temperature of 2 degrees. That's irrelevant. I'm talking about the 10.5 degree warming of the sea off the Labrador coast. I'm talking about the 5 degrees Celsius warming last year, extreme warming. And I think the emphasis of this community on mean temperature warming is not irrelevant. I mean, obviously we do it because that's what the models say, but it's the extreme, and I think we should emphasize extreme temperatures more. And if you look at that, we've well exceeded 2 degrees Celsius, well exceeded. So emphasize that, please.
Yeah, I just want to kind of just pick up on a couple of points that made. I want to just say, I'm really pleased that Robert Tulip, who was mentioned earlier as being the kind of the provocateur for today's event, has brought up the issue of ethics, because it's something which kind of has a thread that runs through this whole discourse. And I think probably there would be very little dispute amongst the people that are involved here today and are listening online, that whatever we do about climate change, we need to have some sort of sense of justice, some sort of sense of equity in our approaches going forward. But there's a but, and there's always a but. And it goes back to my comment earlier on about climate change waits for no man. So these issues about ethics and fairness and justice and so on and so forth, they are really, really important, but we mustn't allow them to become barriers that prevent us from taking appropriate action at the speed and scale that is necessary on the ground and in the atmosphere to prevent the sorts of challenges that have been referred to, that we're all aware of, that just mentioned. And, you know, it is not so much about average temperature. I mean, even the whole concept of climate, you know, people don't live in a climate, they live in the weather, you know, with what's going on outside the window right now. The climate's an average over 30 years. And, you know, a comment was somebody made to the other day about the fact that, well, you know, you just need a couple of major floods in Bangladesh over a couple of years where the land is completely flooded, and it destroys the salt water, will completely destroy the fertility of the land. So even when the water has receded and it's no longer flooded, the people can't survive, they can't run their normal lives, their food support has gone, and the whole thing has become a disaster. So the mean and the average is important, but these extreme events are the catalysts for the crisis, for the emergencies that we're all facing. And the fundamental problem that we've all got now, when you look at the international approach to this, is that climate emergency, sadly, right now, is an emergency in name only. And we've got to do, as Woulter was saying before, we've got to bring our resources together to really change that so that it becomes an emergency in reality, and we respond as if it is an emergency, which it is.
Woulter, do you have any further comments?
Well, my pledge is about a next step, a major one. You need one document between now and then, one document, a basic document. Limits Through Growth, in 1972 published, had about 10 forerunners. And then it was concluded by the executive committee that these all had to be combined into one document, because otherwise the message was impossible. So if I hear 10 different stories here, you're in for trouble. So the next plan has to be about one document, call it one document, the report from climate repair community to the world, because that we can hand over to the president of this, the chairman of that, the group over there, the NGOs over there. I hear beautiful stories about how you all think, and alarming stories, how terrible everything is. Honestly, I've heard these stories for 50 years, and I'm stiff bored about it time and again, because I say, please, scientists, I've been a professor in Berlin and Vienna. And what I did, my only job was to talk to students for a full day. And I motivated them to move into political action. So that's what we did in Germany, creating institutions. In the Netherlands, in France, in Sweden, we created institutions and Plan B and Plan C, which was, we need the document, we need the plan. I heard you talking about how to work with the local communities in the north. That was you, huh? And the plan, and then the next question is the plan there? You had a plan, you have a plan there, but the community has no plan there. And if we want to travel to Sami land, which I think is maybe important, then it should not be an incidental journey, but it should be a part of the plan.
Actually, one of the questions, so a question that's on the chat is, what about the conflict of opinions with indigenous populations amongst themselves?
Well, that's what you heard.
Is there a single thing called the indigenous population?
Of course, well, you've done the job
I can
there.
tell you about our experience. There's no single opinion, and you'll find people that go from one extreme to the other. One are worried about losing their mining operation or oil rig that gives jobs to the local community. The other ones are worried about sea ice and hunting, fishing, and traveling through sea ice. What I can say is that there are organizations, you don't need to talk to everyone. There are organizations that you can talk to and that will find a solution. In principle, we have to understand that these people have received 50 years of the Western solutions, going in and trying to do stuff and going away and leaving a lot of rubbish behind. So we need to be aware of that, and we need to listen to these people.
But the point is, it has to be a part of a bigger plan.
Absolutely.
And the plan is what is needed. So there must be a plan B, and with a community of the few hundred people who all together will create a power, influence. That's the point. And there we have to store all the opinions and try to find the common denominator. That is the thing that will raise the interest with all parties in Europe and in all over the world. In the Club of Rome, we are a global organization, a small one, 150 people in the think tank and about 40,000 people in the chapters. But that's enough to create a second plan and a third plan and so on. But you need a second plan. The research here is perfect. The technology has to be developed. But then the plan about political power is Plan B or Plan C. And I don't hear you talking about that. And I would like to advocate for a meeting where we sit around a table for a week. I give you an example. Limits Growth got its first organization in Hungary, believe it or not. The Hungarian communist government in 1974 said, we offer you free space for a full week at Lake Balaton. And at Lake Balaton, the Balaton group, still chaired by Dennis Meadows, came together, a few hundred members, and they allocated their work, their research, their sources to the Balaton group, out of which grew an enormous influence on politics. So take the example, the Lake District group here, or whatever. No, not in England, of course, but somewhere in Europe, don't you think? Must be in Europe, not in England. No. England is fun, of course, but you have to do it elsewhere. Where are you from?
So,
are you from? Toscane. Oh, okay. Okay, Lake Trasimeno. Yes, yeah. Excellent idea.
Okay.
Cortona. Yes.
So I've been very, very pleased with the engagement we've had today, both here in the room and online and over lunch and last night in the pub. And we ought to be doing this kind of thing more often. It is really good, I think, to do things face to face. It's quite tricky having the hybrid model, trying to get people online engaged with our discussions here. I hope you've had a reasonable experience. We've tried our best. Thank you very, very much for being with us online, and it's been great having you. Thank you, Robert and Woulter, for being in front of camera for the last 45 minutes or so, helping us sum up. Really thank you all for coming along. I'm a bit ahead of schedule because I think we're all ready for a bit of a stretch of legs, and those online can go and have a beer, but we might have one as well. So just to say, thank you all very much, and we'll look forward to the next event, wherever it might happen to be.